Life is a journey with different roads. Life is a journey with different roads. Sometimes you feel high, sometimes you feel low. Sometimes it rains, while sometimes it sunshines. So, whenever you are feeling low, my dear students, just know that it will come to pass. So, keep your chin up and let the world see your shine. So, hello, my shimmering stars. I, Shaurya, is going to start our next lecture on isomerism. So students, hopefully you have covered the previous lecture of organic chemistry, that is IUPAC nomenclature. So today we are proceeding towards our next chapter, isomerism. First of all, students, keep your notebooks in your hand and get ready because we are going to do a lot of topics today which are very interesting. So let us start with our very first segment, that is, what do you mean by isomerism? Students, whenever you are studying chemistry, try to understand each term by splitting it into two parts. If I split isomerism, what I see here is iso. So, you have already seen isobar, isotopes in your physical chemistry. You would have understood these terms in your physical chemistry. So, what was iso there? Iso refers to as same. Iso refers to as same. Now, what is same here? Question arises in our mind, what is same here? We are going to see that organic compounds which have same molecular formula but at least one different property are referred to as isomers of each other. Now that one different property can be physical or it can be chemical. And this phenomena, students, is known as isomerism. So what I am saying, the organic compounds which have same molecular formula but at least one different property. Now this one different property can be your physical, it can be your chemical. Physical or chemical, students. Just try to understand that these are isomers of each other, and this phenomena, students, is isomerism. Clear? Now, let us take one example for isomerism to clear you. If I take alcohol and ether, that would define it very correctly. See, I am taking an example of alcohol like CH3, CH2, OH, and ether, that is CH3O, CH3. So this is my very first example that I'm going to explain for isomers. See, if I talk about both of these molecular formula, if I'm taking this as of my first compound, so I would say that here basically there are 2 carbon atoms. How many hydrogen atoms are present? So I would say 3 plus 2 plus 1, that means 6 hydrogen atoms, while 1 oxygen atom is present. If I talk about this compound, students, I have again 2 carbon atoms with me and 6 hydrogen and 1 oxygen. So I would say for both of these cases, the molecular formula which I am writing with MF comes out to be same. Now, does that satisfy the condition for isomerism? Yes, it is satisfying that it has same molecular formula, but as I told you, it should have at least one different property. So, you know, when we see its physical or chemical properties, first property which we see is physical state. Alcohols are basically liquid, while if I talk about ether, they are basically gaseous. And if I talk about its chemical reaction, students, I would say when, you know, reacted with sodium, it liberates H2 gas, while there is no reaction for the case of ether. And if I talk about the reaction with HI, I would say that it liberates CH3, CH2I, and it liberates CH3I. So you can observe, like I talked about sodium. So when there was a reaction with sodium, it liberated H2 gas while there was no reaction. So there is at least one different property which we saw here, or I would say if I talk about physical state, it is liquid while it is gaseous. So there is a change in physical state. So we require only one physical property for them to be known as isomerism, for them to be known as isomers. But molecular formula should remain same, students. Clear? So you can here also write this is alcohol while this is ether. Clear, students? So this was our very first, very first segment that we got to know what are isomerism and what are isomers of each other. Now comes the classification. If I'm going to classify isomerism, I will classify into two basic categories. That it is going to be, first of all, structural isomerism. Another one is stereoisomerism. Now, as the name suggests, there would be something different. What I'm saying is, if I'm talking that there is a difference in structure, so that means I'm talking about structural isomerism. If I'm talking about there is a difference in the spatial arrangements of the groups present in a molecule, then I'm talking about stereoisomerism. So on the basis of the difference, we have classified isomerism into two basic categories. First one is the structural, where I talk about that there is difference in structure, or I would say here different connectivity is observed. Students, I am using a word connectivity. Connectivity means to connect with the different atoms. Later on, I'm going to explain you what I'm referring to here with the help of some of the examples, right? So I would say difference in structure, or I would say different connectivity of atoms. Different connectivity. Okay, now if I talk about stereoisomerism, I would say there is a different spatial arrangements of groups in the space. Spatial arrangements refers to the atoms arrangement in the space. Spatial is space. So I would say arrangement of, different arrangement of, sorry, add a word here, different arrangement of atoms or groups in space. Basically, it is kind of a 3D, but we are going to explain you here. If I talk about a structural isomerism, these are further classified into 5 basic subcategories. They are chain isomerism, positional isomerism, functional isomerism, metamerism, and tautomerism. Again, when I am talking about the on which basis I have been classifying them, so the basis is the difference. Like there was a difference in the structure, so the name arised structural isomerism. Now, when there will be a difference in chain, that will be known as chain isomerism. When there will be difference in position, that will be referred to as positional isomerism. When there is difference in the functional group, that will be referred to as functional isomerism. And the other last two, we will discuss it later on, but that will come across. Like here, if I talk about these 3 basic categories, we can classify on their name only. But if I talk about metamerism and tautomerism, it is quite different from these 3 basic. Okay. And if I come across stereoisomerism, so I would say these are further classified into geometrical and optical. Okay. Now, these two are also very, very important. First of all, we are going to start with our very first category, that is structural isomerism. So students, as the name suggests, structural isomerism, so there will be a difference in the structure. If I talk about its definition, so compounds having same molecular formula. Like this is the basic necessity for any compounds to be known as isomers of each other, that they should have same molecular formula. Other than this, what we are observing, there should be at least one different property. So what is the different property? The different property is that but different structures, that is different arrangement of atoms within the molecule. Now some of you will say, ma'am, in the stereoisomerism you also told that difference in the arrangement of atoms, but that was in the space. Clear? Here we are talking about different arrangement of atoms within the molecule. Clear? Are called structural isomers, and the phenomena is structural isomerism. Now let us talk about the very first category. let us talk about the very first category, that is chain isomerism. So the compounds having same molecular formula, again the basic necessity condition, right? But different chain of carbon atoms. Now here, different chain of carbon atoms can be classified further into two categories. One is different size of parent chain or parent chain, or I would say different size of side chain. It can be any of these two conditions. Then they are chain isomers of each other. Students, one thing you need to note down here. Kindly put a note over here. I would put a box and we'll write here. You have to note that nature of functional groups, multiple bond, that means double bond or triple bond, or substituents will remain same. Now what I meant by this term, that nature of functional group, double bond, triple bond or substituent should remain same. That means if I am talking about alcohol, I am talking about alcohol in the another compound also. It would not be like this if first compound is of carboxylic acid and another one is of ether. No. There should be same nature of the functional group. If I am talking about first compound, if it is having double bond, then second compound should also have a double bond. Nature should be same. If I am talking that my first compound is having a side chain of CH3, another one should also have. So just the difference will be in the size of the parent chain or the side chain. That's it. Nature should remain same. Now let us take first example. If I talk about the very first example, let us take carbon atom 1. Now, if I am taking a very basic example, that is CH4, where carbon is only 1. Now, please let me tell that CH4, does it have any chain isomer with any of the compound? No, it cannot form any chain isomer because it is already 1 carbon. To form a chain isomer, at least it should have more carbon so that there will be difference in chain. So it cannot show any of the chain isomers. If I talk about another one, that is CH3, single bond CH3. Now, does here, the very basic condition is molecular formula should remain same. If I talk about these two cases, now let us see this case and this case. Are molecular formula same? No. So these are no isomers of each other. The basic categories doesn't arise here because these are not isomers, so why to move on to the types, right? But if I talk about CH3, single bond CH3, and I say please draw a structure for chain isomer of this, so you would say no ma'am, it cannot make any of the chain isomer because it has 2 carbons, and from 2 carbons we cannot make any chain isomer because parent chain size is 2 carbon atoms. It can't change, right? Now, if I talk about the next one, that is CH3, CH2, CH3. Now, in this case, students, does it show chain isomer? No, again, it cannot show because 3 carbons can't show. But now let us see the case of 4 carbon atoms. You'll clearly understand why these 3 were not making any chain isomers. So, see, if I talk about 4 carbon atoms, I would say CH3, CH2, CH2, CH3, right? And one more with 4 carbon atoms only, CH3, CH, CH3, CH3. Now students, let us count the atoms here so that let us see the molecular formula here for both of these compounds. If I talk about the very first compound, there are basically 4 carbon atoms, right? So here are 4 carbon atoms. How many hydrogen? 3 plus 2, 5. 5 plus 2, 7. 7 plus 3 is 10. So C4H10. If I talk about this compound, how many carbon atoms are there? Ma'am, total 4 carbon atoms. How many hydrogens are there? 3 plus 1, 4. 4 plus is 3 is 7. 7 plus 3 is 10. Again, students, both of these have same molecular formula. The very first condition, that molecular formula should be same so that these are isomers. Now, to check whether it is chain isomers of each other or not, first of all, we need to identify the parent chain. To identify the parent chain, we know that parent chain is basically for the, longest parent chain is observed for the maximum number of carbon atoms. So if I say here 1, 2, 3, 4, here my parent chain is of 4 carbon atoms, students, right? If I talk about this case, I would say 1, 2, 2, 3. Here my parent chain is of 3 carbon atoms, and CH3 is the extra group which is attached over the second carbon atom. So if I see in both of these cases, let us say this is my first compound and let us say this is my second compound. So I would say there is a difference in size of parent chain. Difference in size of parent chain. Hence, students, I would say when there is a difference in size of parent chain or the size of side chain, then they will be known as chain isomers of each other, which I am writing as CI of each other. Clear? Now let us take one more example to clarify this concept more clearly. If I take one more example, let us see here. Okay. Now this is my example. You can either put this methyl group over here or there. That is up to you. What I want to explain you here is, see, what is the parent chain here? If I draw the parent chain, I would say this is the parent chain. Okay. And in this structure, this is the parent chain. These are parent chain. And both of them are same, their sizes are same. Okay, now if I talk about side chain, that means the extra group that is attached over here. So what I observe is, I observe basically it's carbon, we know that according to the bond line notation. So this is my side chain over here, and if I talk about this case, this is carbon, so this is my side chain, while this is my side chain. So what I am observing here is, here basically there are 2 carbon attached. That means it is ethyl group. You're getting my point. Here this side chain has ethyl group attached. But if I talk about these side chain, students, then what I observe here, they have methyl group attached over here. They have single carbon, that means methyl group attached over here. So what do we observe here? That there is same parent chain but difference in the side chain, students. Here what are we observing? That parent chain is same but side chain is different. So this is the case when it is also known as chain isomer. It can be either the difference in the parent chain or the difference in the side chain. So we have seen in this case that side chain size of side chain is different. Now let us take one more example like this to clarify it. Okay, this concept more. So if I take this example here, like this you can draw yourselves also. Okay, let us take this example. Now if I take this example again, I'm going to identify my parent chain. I would say, ma'am, this is my parent chain here, which consists of maximum number of carbon atoms. If I talk about this compound, this is my parent chain. Now if I talk about, I'm writing with red only, parent chain, right? If I talk about side chain, my dear students, I would say, again, this is of 2 carbon atoms, so it is ethyl. This is of methyl, while this is of methyl. So here there is 1 carbon atom, here there is 2 carbon atoms. So here there is difference in size of side chain. So now are you getting my point, that what is the difference in the side chain or the difference in the parent chain? Now let us take one more example. Three, 4, 5, 6. I'm taking parent chain of size 6 just to make you understand. Now what I'm doing here is, Okay. Now students, let us see both of these examples. Here again, if I take the case here, the parent chain comprises of 6 carbon atoms. Here also the parent chain comprises of 6 carbon atoms. When I talk about the side chain, here we can see the ethyl group, while if I take here, these are two different methyl groups. Now this bond is attached with carbon, not with hydrogen. Don't get confused. So here what are we observing? That difference in the size of side chain. Clear? So students, these are basically the example of chain isomerism. Now comes our next category, that is positional isomerism. So if I talk about positional isomerisms, what do I observe here? The compounds with same molecular formula, again the basic necessity condition that we need to remember. If I talk about the previous cases also, you can even calculate for each of these cases the molecular formula is coming out to be same. Like for both of these, molecular formula is same. Count the carbon atoms, count the hydrogen atoms, so you'll get your answer, right? So if I talk about positional isomerism, again there is a same molecular formula. Now with same size of parent chain, listen to this carefully. Now you are getting the same size of parent chain or the same size of side chain, but what is the difference here? Difference is in its name, that is position. So having different position of functional group, multiple bond, substituents. Now what are you going to observe is that there is now same molecular formula, same size of parent chain, same size of side chain, difference lies in the position. Like in the very first case, you will observe that methyl group is attached to second carbon atom, but if I change its position from second carbon atom to fourth carbon atom, that means there is a change in position of the substituent, or change in the number of the double bond. If I talk about double bond is present between second and third carbon atom, but in the second compound it is present between fourth and fifth carbon atom, so there is a change in position of the double bond. So that is referred to as position isomers. Now let us take an example for position isomers. Now you will say, ma'am, this is chain isomers. No, chain isomers were a quite different concept. We took here ethyl group and their methyl groups were present. Side chain size were different. In the very first case, there were 2 carbon atoms. In the second one, there was methyl, so 1 carbon atom. Here, what you are saying, here, this is parent chain. This is parent chain. 3 carbon atoms, 3 carbon atoms. If I talk about the side chain, 1 carbon atom, 1 carbon atom. If I talk about the side chain, 1 carbon atom, 1 carbon atom. The sizes of the parent chain as well as the size of the side chain are same in both of these cases. But if I take the previous case, see here, if I take this case, there are 2 carbon atoms here and there is 1 carbon atom over here. So here 2 carbon atom size is different while 1 is different. But if I take this example here, there are 1 carbon atom, 1 carbon atom. That means it is not a chain isomer of each other. So now what we are observing is, if I am going to do numbering of these, okay, here it is present, extra group is present over this compound, so it is 1. This carbon, so it is 1, this is 2, this is 3. If I talk about this, it can be 1, 2 and 3. So what do I observe here? That methyl groups are present over the first carbon atom. Both of the methyl groups are present over the first carbon atom. But if I take this case, one methyl group is present over the first carbon atom, but the another one is present over the second carbon atom. So if I say the common ones, like 1, 1, put a hand over here, it is also present on 1, it is also present on the 1. What is the basic difference that you are observing? That another one is present over the 1, while the another one is present over the second. So there is a difference in the position, difference in the number of the position of the carbon atom. So that means these are position isomer of each other. So I would say these are pi of each other. In short, position isomers of each other. Now let us take one more example to clarify your thoughts. Okay students, now if I take this case, you can clearly observe that the parent chain comprises of 6 carbon atoms. This is our parent chain. If I talk about this case, this is our parent chain. If I see this case, this is our parent chain. If I see this case, this is our parent chain. Now if I talk about the side chain, each one has methyl groups. That means side chain size is also equal, but the number Here the position is different. Now let us do the numbering. This is first, this is second, third, fourth, fifth, sixth. If I see here 1 2 3 4 5 6, if I see here 1 2 3 4 5 6, if I see here 1 2 3 4 5 and 6. Now see the numbering. Here both of the methyl groups are present over the first carbon atom. Here one is present over the first, while another one is present over the second carbon atom. While if I take this case, one is present over the first and another one on the third carbon atom. And if I take this case, one is present on the first and another one on the fourth carbon atom. Now this is bond line notation. This is carbon, this is carbon, this is carbon, this is carbon, carbon, carbon. Don't get confused. This we have already done in the previous lecture, the bond line notations. All of these are carbons. All of these are carbons over here. Each end represents a carbon atom. Clear? So this were the case of students' position isomers. Now let us take one more case to define it more clearly. Again, I am taking a case of 6 carbon atoms as a parent chain. You can either take 5 or 4. It is up to you. Okay. Okay, students, let us see this case. If I see here, how many carbon atoms are present in the parent chain? 1, 2, 3, 4, 5, 6, right? If I see this case, 1, 2, 3, 4, 5, 6. 6 carbon atoms are present in the parent chain. That means the size of the parent chain is same. Now let us see the side chain. Methyl group, 1 carbon atom. That means side chain size is also same. Now what is the difference here? We can observe that if I do the numbering of these carbon atoms, 1, 2, 3, 4, 5, 6. The methyl group is present over the second carbon atom. While if I do the numbering of these carbon atoms, 1, 2, 3, 4, 5, 6. What I observe here is that the methyl group is present over the third carbon atom. So here there is a difference in the position of CH3 group. Here it is present of the second, and in another case we can see on the third. So it is refers to as positional isomers of each other. Now let us take one last case. Okay, students, now this is your case. Either you can take of ethyl group also. I have taken of methyl group. These are again same. The parent chains are sizes are same, side chain sizes are same, just the positions are different. Clear? Now let us see the next case, students. The next comes out to be the functional isomerism. Now, what do you mean by functional isomerism? We have seen when there is difference in the chain, it is chain isomerism. When there is difference in the position, it is positional isomerism. Now, when there is a difference in the functional group, it is refers to as functional isomerism. It is quite simple. The compounds having same molecular formula. This is the basic necessity condition. Students, do not forget this. Do not forget this. But different functional groups in the molecules. Let us see the examples. If I talk about the very first example, you can see here, this is alcohol, while this is ether, which we took example in the very starting, right? So what do we observe here? If I see the molecular formula for both of these cases, that does it satisfy the condition to be an isomer? To be an isomer, it should have same molecular formula, right? So if I see this, so there are basically 2 carbon atoms and 6 hydrogen atoms, while 1 oxygen atom. While if I see this case, again 2 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. Molecular formulas are same and different groups are present. Now what are the different functional groups? Here OH is present, while here you can see besides oxygen in both of the sides there is an alkyl group, right? If I talk about the second case, this is our aldehyde group, CHO group. This is our aldehyde, while this is ketonic group. Now if I talk about ketone, this is our ketone when C double bond O is there and besides it both have the alkyl groups. And here you can see that here you can clearly observe that with C double bond O, one side is H, another side is alkyl group, as you can see here. Now you can calculate the molecular formula for both of these cases. Again, check the carbon atoms, check the hydrogen atom, check the oxygen atom, they are same. The difference is that it contains CHO group while it contains C double bond O group. Clear? Now comes the next case, that is carboxylic acid and ester. This is our carboxylic acid. Carboxylic acid, while this is students ester. Here you can see again the molecular formula is same, but there is difference in the functional group. We have already covered the functional group in the IUPAC. What are functional groups? We have seen the very basic definition for them, right? Now comes the next category. You can see this case here, students. CH3 will not come. Kindly cut this. Okay. Now you see this is cyanide. When the alkyl group is connected with the carbon, it is cyanide group. When it is connected with the nitrogen alkyl group, it is isocyanide. Kindly correct this. Here only C will come, not H3. Clear? Now if I talk about this case, this is thiol or thioalcohol. And if I talk about this case, this is thioether. Just like alcohol, we see OH group, here we see SH group. Just like ether, here we used to see oxygen group, now we are seeing sulfur group. Clear, students? Now this was functional isomerism when there was a difference in functional groups, right? Now comes the part of functional isomerism. It is a kind of functional isomerism, the special kind of functional isomerism, that is ring chain isomerism. Now what do you mean by ring chain isomerism? The isomerism which arises due to difference in mode of linking. It is quite different and easy also. Here you will see the difference in mode of linking of carbon atoms in ring or open chain. Now what do you mean by linking here? See, one is this, another one is this. These are ring chain isomers of each other. But why you can correct it, here you will see degree of unsaturation should be same. It is like this. Now it is correct. It is like this. See, you see degree of unsaturation. What do you mean by degree of unsaturation? Number of pi bonds or ring present in a compound. So here one ring is present, here one double bond is present. Both of these have degree of unsaturation as 1. If I talk about molecular formula, students, you can even check the molecular formula. Here there are 3 carbon atoms. If I talk about hydrogen atoms, let us see that also. See, carbon, carbon, carbon. Now talk about hydrogen. How many hydrogen? 2 bonds are already made. How many bonds are left? 2, because carbon can make only 4 bonds. Again, this will have 2, this will have 2. Now if I check here, students, what I observe is basically, see, 2 plus 2, 4, 4 plus 2 is 6. 6 hydrogen. If I see this case, 3 plus 1 is 4, 4 plus 2 is 6. That means carbon atoms are same, hydrogen atoms are same. But you will say, ma'am, it contains ring, it contains double bond. See, that means degree of unsaturation. It has a ring, it has a double bond. That means degree of unsaturation is same. Molecular formula is same. Clear? But here linkage is different. Here you can see that first carbon atom is linked with the third carbon atom. But if here I see, here it is open chain compound, first is not linked with the third carbon atom. So the isomerism which arises due to difference in mode of linking of carbon atoms in the ring or the open chain is known as ring chain isomer. Now let us take one more example. Let us say this is our first compound. Let us say this is our second compound. And if I talk about the third compound, I would say this is my third compound. Now, let us compare the first and the third compound. First and third compound are ring chain isomers of each other. Second and third compound are the ring chain isomers of each other. Not first and second. Not first and second. One should be ring, another should be open chain. Clearly, linkage should be different, student. Here, linkage is again the same. First is attached over the last carbon atom. First is attached over the last. I am talking about first and the third element. Third compound. Both of these are ring chain isomers of each other. Second and third are ring chain isomers of each other. But if I talk about first and second, these are chain isomers of each other. What were chain isomers? When there was a difference in the parent chain. You can see the parent chain here is of 4 carbon atoms, but here it is of 3 carbon atoms. So there is a difference in the parent chain. Hence first and second are chain isomers of each other, while first and third, second and third are ring chain isomers. Hope so it is clear to you. Now let us see the next kind, that is metamerism, students. What do you mean by metamerism? Compounds having same molecular formula. Now molecular formula is same, but different number of carbon atoms on either side of the functional group, or I would say polyvalent functional group, or I would say polyvalent functional group. are known as metamers and the phenomena is known as metamerism. To clarify it, let us see one example. C2H5O, C2H5. One more example, CH3O, CH2, CH2, CH3. Now these are metamers of each other. What I am saying, you have to see the polyvalent functional group. For example, oxygen is here the polyvalent functional group which is connecting towards, on both of the sides. What you see on both of the sides, there should be different number of carbon atoms. If I see in the first compound, on this side there is 2 carbon atoms, on this side there is 2 carbon atoms. But if I see in this compound, on this side it is 1 carbon atom, but on this side there are 3 carbon atoms. Right? Check the molecular formula. Molecular formula is same because both of these have 4 carbon atoms. See, if I talk about hydrogen, they have 10 hydrogen. In this case also you can see they have 10 hydrogen, 1 oxygen. That means molecular formula is same, but where the difference arises, the difference arises in the atoms that are present over the polyvalent functional group. On both of the sides of the polyvalent functional group, they should be different. The number should be different. Here these are 2, 2. Here it is 1 and 5. Now let us take one more example over here. I'm going to write over here only. Wait. Let us see this example. If I see this example, what do you observe here? There are 2 carbon atoms over here and there is 1 carbon atom over here. But if I see this case, there is 1 carbon atom over here and 2 carbon. You will say, ma'am, this is same. No. See the linkage with the polyvalent functional group. Here with oxygen, it is attached CH3, and with sulfur it is attached CH3 CH2. But here with oxygen it is attached CH2 CH3, while with sulfur it is attached CH3. You can see the difference. Or either consider any one of these. If you are looking at the oxygen, you are seeing CH3. If you are looking at oxygen, you are looking at CH2 CH3. So the number of atoms on either sides are again different. These are not same. It is very important. While quite different, students get confused. They are same. No, these are not same. You need to check the linkages through which it is attached. Check the linkage. That is most important here. Now here also you can see basically there are 2 carbon atoms over here and 1 carbon atom over here. If I see here with oxygen 1 carbon atom, with oxygen 2 carbon atom, just the similar case like this, right? You have to check what? You have to check the number of carbon atoms on the either side. Now let us see this case again. With oxygen, here is CH3 while we have this chain. If I see here with oxygen, it is CH2 CH3 while we have this chain. But if you'll check their molecular formula, students, molecular formula will come out same. Clear, students? Molecular formula will come out same. Now students, I am going to move forward towards our next category, that is referred to as Tautomerism. What do you mean by Tautomerism? Let us see. When 2 or more consequently distinct compounds are in dynamic equilibrium because of shift of an atom. Here, this is most important line that you need to remember. Here is an shift of an atom, and that atom is generally a proton. Okay, from one place to another in a molecule, and both of these structure will be in equilibrium with each other. It is known as, the process is known as tautomerism. Now let us take its example, and with the help of example I am going to show you the shift of the proton from one atom towards another atom. So students, now let us take case for the tautomerism. Now first of all, let me tell you, tautomerism occurs in carbonyl compounds, and carbonyl compounds contain this carbonyl group, C double bond O. Now this group is present in both cases, in aldehyde as well as in ketones. So what I can say, this is present in both of the cases, in aldehyde and in ketone. So students, if I talk about, the functional group for aldehyde, that is CHO, right? So how does it looks like? It looks like this. And if I talk about ketonic group, it looks like this, right? So this C double bond O is present in both of these structures, here also, here also. What is the basic difference that we can observe here? One alkyl group is there and one hydrogen, while in ketone both alkyl groups are there, and these alkyl groups can be same or can be different. Now let us see how tautomerism occurs in aldehyde and ketone. Now one thing you need to mention over here is that alpha hydrogen must be present for tautomerism to exist. Now first of all, I'm just showing you the reactions. Then I will move forward towards the mechanism portion, right? Okay. Now let us see the very first reaction will be the tautomerism in aldehydes. Now, for the case of aldehydes, I am taking example CH3 C double bond OH. Students, this is aldehyde and it remains in dynamic equilibrium with the enol form. Now, what is the enol form over here? CH2 double bond CHOH. This is the enol form. Now, why it is referred to as enol form? Because it contains double bond as well as OH group. En stands for ene, that is double bond. Ol stands for alcoholic group, that is the OH group. Now, if I talk about the ketone, students, now I am taking the case for ketone, that is CH3 C double bond O CH3. This is my ketone. Now, its enol form basically is CH2 double bond COH CH3. Clear, students? Now I am going to explain you how these are converted into their enol forms. To understand this, first we need to understand the mechanism. Now, what is the mechanism? I am taking both of these cases for aldehyde as well as for ketones. Now, if I talk about aldehyde, students, basically aldehyde is CH3 C double bond OH, right? And I can also write this CH3 as CH2H, right? I can write this CH3 as CH2H in such a way, right? Now, students, what happens? It occurs in basic medium. In basic medium, OH negative ion is present. Now, OH negative ion gives its electron to hydrogen and so they form water, while hydrogen, is bonded with this. It is bonded with CH2, so it gives its electrons to CH2. Now, when CH2 receives electron, it carries a negative charge. Whenever we get electron, we get a negative charge because electrons are negative in nature. So, CH2 negative will come, then C double bond OH. It is present. Now, students, come the resonance. Here, resonance occurs. From more electronegative atom, it will move. Like what I am going to tell you, not electronegative atom, from electron density. We are seeing the movement of electrons with the help of electron density. Like you can see, this negative charge contains electrons. So, the electrons that are open up will move, okay, from one position over the another position. It will do resonance. This will come over here and make a bond, while this bond will break over oxygen atom. This is the resonance over here. Don't worry, in the coming videos in the GOC section, when we are going to do the lecture on general organic chemistry, we will understand resonance in detail. But first of all, you need to understand what is happening over here. Now, what happens, students? CH2, now this electron, these electrons are broken over here, so it makes a double bond over here, and this double bond is broken over oxygen. That means electrons are carried to oxygen, and when oxygen gets some electrons, it carries a negative charge. So we are getting this case. Now we know that, water was formed here, right? So here again water is also present, right? Now water contains H positive as well as OH negative ions. So what is the next step? These H positives are going to attack the O negative ions, forming enol form, that is CH2 double bond C OH, and then comes H over here. Now this is, students, enol form. This is the enol form for the case of aldehyde, and you will say that ma'am, H positive attacks O negative, but where does OH negative goes? It again starts to react with the next molecule like we did in the starting, right? So this was the case for aldehyde. Now let us take the case of ketone, students. Let us take the case of ketone over here. If I talk about ketone is basically CH3 C double bond O CH3. I am taking the simplest ketone, right? Now what happens, students? It also occurs in OH negative, that means the basic medium. Now what happens here? Which is the alpha hydrogen over here? Let me mention that also, because I told you that here alpha hydrogen plays an important role. Here we have mentioned this hydrogen separately. Why the reaction doesn't start with this hydrogen? Because this hydrogen is not an alpha hydrogen. Why? See, this carbonyl group is attached to a carbon. This carbon is alpha carbon, and alpha carbon contains hydrogen. These hydrogens are alpha hydrogen. So you need to remember, carbonyl group is attached to a carbon. That carbon is alpha carbon, and hydrogens attached to the alpha carbon are alpha hydrogen. Not this hydrogen. It is not attached to a carbon that is attached to C double bond O. So it is not a alpha hydrogen. Now here, if I talk about alpha hydrogen, these can be alpha hydrogen, where these can be alpha hydrogen. I can write this as CH2H, or you can write this as CH2H. How many alpha hydrogens are present over here? 6. Because there are 2 carbons which are bonded with C double bond O. Both of these carbons are alpha carbons, and the hydrogen attached to these alpha carbons are alpha hydrogens, right? Now what happens is, again, it will give its electrons, it will break its bond over here, electrons will move to CH2, it will become negative. Here C double bond O, CH3, and water is formed. Now what happens? Resonance occur. This is broken over here, double bond breaks over oxygen, CH2, double bond carbon, O negative, CH3. Now as you know, water contains H positive ions, so what will form here? CH2, double bond C, OH, CH3. This is the enol form for the case of ketone, students. Clear? Now one thing that you need to understand is which form is more stable. You know, if I talk about aldehyde or ketone and enol form, I would say aldehyde and ketone are more stable as compared to enol form. Why, students? Because in enol form, what do you observe? That there is basically double bond between carbon-carbon. But if I talk about aldehyde, there is a double bond between carbon-oxygen. And if I talk about ketone, there is a double bond between carbon-oxygen again. So carbon-oxygen bonds are more stable as compared to carbon-carbon double bond. Hence, aldehyde and ketonic form are more stable than the enolic form. Clear, students? Now let us move towards our next topic, students. So this sums up our structural isomerism portion. Now we are going to start with some questions based on structural isomerism. Clear? We have already covered chain isomerism, positional isomerism, functional isomerism, metamerism, and tautomerism. Hope so you have understood all of these very clearly. Now let us apply to the question section. See, CH3, CHOH, CH2, CHO. Here this is OH as a group and CHO as a group. Okay, and CH3, CH2, CH2, COH. Here this is COOH as a group, carboxylic acid. Constitute a pair of, we need to tell that these compounds constitute a pair of which of the following? A is position isomers, B is metamers, C is optical isomers, while D is functional isomers. So students, as you can see that here basically are 2 functional groups, OH as well as CHO. CHO is aldehyde, OH is alcoholic group. And here what do we observe? We observe carboxylic acid, that is COOH. Now, you know that first A option says position isomers. Position isomers, we have studied that nature of functional group remains same. That means if I am taking both of the cases, in both of the cases, if I am talking about alcohol, I have to talk about alcohol in another case also. If I am taking about ketone, in another compound ketone should be present. But here what happens? In the very first compound we are seeing alcohol and aldehyde, in the second one we are seeing carboxylic acid. That means nature of functional groups get changed over here. So it can't be position isomers. Now if I talk about metamers, what were metamers? Metamers were the one in which polyvalent functional group contained different number of carbon atoms on either side, right? So it can't be metamers again. Right, now comes optical isomers. You would say that, ma'am, we have not yet studied about optical isomers, so don't worry, but you have studied this thing that optical isomers comes under the category of stereoisomers, and stereoisomers are the one in which we see the different arrangement of atoms in the space, right? So it again can't be optical isomers. Now comes option number D. We no need to think over it because it is functional isomer, because we can see in both of the cases there are different functional groups present, right? So the answer is going to be option number D, my dear students. Answer is your option number D. Okay, now let us see the next question. The minimum number of carbon atoms present in any organic compound to show chain isomerism is. Now this question is quite different from the previous one. Here they are asking us minimum how many carbon atoms can actually show chain isomerism. Now if you have understood the lecture from the very start very clearly, the answer is in front of you. I told you the case of CH4, if you remember. If you remember, I took the case of CH4, then I took the case of CH3, single bond CH3, then I took the case of CH3, CH2, CH3, and third case was CH3, CH2, CH2, CH3, and students, CH3, CH, CH3, here came CH3. If you remember, on the very first page, we have discussed this topic. I told you that in these three cases, chain isomerism is not possible. Why it is not possible? Because we at least require 4 carbon atoms. Like you can see, for even 3 carbon atoms, you cannot, change the size of parent chain. You need to either change the size of parent chain or the size of the side chain. In these cases, in which 4 carbon atoms are present, you can clearly see this is basically what? This is basically the straight chain, and if I talk about this case, here we can see the parent chains of 3 carbon atoms. Hence, we require basic 4 carbon atoms to make these structures. Here also 4 carbon atoms are present. Here also, if we count total number of carbon atoms, 4 carbon atoms are present. Now, to be a chain isomer, the basic condition, it should be an isomer first. That means it should have molecular formula same first. So if I see here 4 carbon atoms over here, 4 carbon atoms over here. Hydrogen, if I'm going to count, is 3 plus 2, 5, 5 plus 2 is 7, 7 plus 3 is 10. If I see here, 3 plus 1 is 4, 4 plus 3 is 7, 7 plus 3 is 10. So these are, chain isomer of each other, and the answer is going to be option number D, that is 4. Clear? Answer is again going to be option number D. So students, now let us proceed towards the next question. Next question is, the simplest pair of compounds exhibiting functional group isomerism have a minimum of. Now, we need to make functional group isomerism, and the simplest can be like, start from the very first carbon, the single carbon atom. Does a single carbon atom, can have different functional groups? No. If I say 2 carbon atoms, yes, I can make a structure. I can make a structure. See, if I say CH3, CH2OH, this is alcohol, and if I say CH3OCH3, it is ether. This is alcohol, this is ether. Now students, this also we have studied in the very first slide of ours, that was isomerism. I took this example in front of you. So here basically there are 2 carbon atoms, here is also 2 carbon atoms, hydrogen are 6, oxygen is 1, oxygen is 1. So with a minimum number of carbon atoms, we can make, we can make what? Functional group isomerism, where functional group is different. Here molecular formula are same, but functional group here is alcoholic group, while here is ether present. So functional groups are different. Hence, answer is going to be from 2 carbon atoms at least we can make the minimum. From minimum number of carbon atoms, here is going to be 2. Again, the answer is going to be option number D. Now students, moving forward towards our next question, that is CH3NH, C2H5 and CH3 thrice N show which type of isomerism? A is position, B is functional, C is chain, and D is none of them. See, position isomer is the one in which the position is going to be different of, side chain, of double bond, of functional group, or of multiple bond. So any of these cases are not present over here, hence it can't be position isomer. It can't be position isomer. I'm very sorry for this. Okay. Now, if I see the case of functional isomer, functional isomers are the one in which functional group is different. If I see the very first case, I can say that it is secondary amine. Here this nitrogen is attached to 2 carbon atoms, so this is secondary amine, and here nitrogen is attached to 3 carbon atoms, so it is tertiary amine. So this is 2 degree amine, this is 3 degree amine, hence the functional groups are different. So when functional groups are different but molecular formula is same, that is referred to as functional isomer. So the answer is going to be option number B. But if I see the case of C option, that is chain isomer refers to the change or difference in the parent chain size or in the side chain size. So that doesn't occur over here. So answer is going to be option number B, students. Clear? Okay, now let us see the next question over here. The next question is the minimum number of carbon atoms in ketone to show metamerism. We have just studied this case. Ketone we have made, no? Simplest case was C. CH3, C double bond O, CH3. Now, we have taken this case for ketone to show metamerism. Here I am talking about metamerism. Sorry for the confusion. I took tautomerism. If I talk about metamerism, in metamerism we are taking for the case of polyvalent functional group, and we need on the either sides the different number of carbon atoms. So the simplest case is ketone group is this. ketone group is this, and I have to make, the different groups on either of the sides. So if I say here CH3 CH2, and if I say here CH2 CH3, this is my first case. And let's take the next case. I would say CH3 C double bond O CH2 CH2 CH3. Now this is going to be, my answer for this. If I check how many carbon atoms I want to this complete for metamerism, 1 2 3 4 and 5. So at least 5 carbon atoms are required, and I have seen that C and D options are almost same, so kindly correct it. C option is 5, right? So how many minimum carbon you need? 1 2 3 4 5. 1 2 3 4 5. So answer is going to be option number C. Clear? Answer is going to be 5. That is option number C. Now let us see, students, the next part. Okay, which similarity is necessary for isomerism? A option is molecular formula, B option is structural formula, C is physical formula, while D is chemical formula. So we know that if there is same molecular formula but at least one different property, it can be either physical or it can be either chemical, then it is referred to as isomerism, right? So molecular formula should be same. Clear, students? So this ends up our first segment, that is the structural isomerism. Now we will move forward towards our next segment, that is stereoisomerism. Now it is going to be very interesting because we are going to imagine now all of the cases in 3D. Now what happens is, as I have told you in the very starting during the classification of isomerism, that stereoisomerisms are the one which have same molecular formula because it is a kind of isomerism. So same molecular formula is seen, but where does the difference arises? The difference arises that they have different relative arrangement of atoms or group in space. They have different arrangement of atoms or groups in space. Now, to explain this, students, I am going to take one example for you. Now, let us see this example. Carbon, double bond carbon, CH3, H, CH3. And the next case is carbon, double bond carbon, CH3, H, CH3, H. Now, these if I consider both of these cases, these are stereoisomers of each other. Why, students? Because here what you will see, the molecular formulas are same. You can clearly see the DU here is same, degree of unsaturation. Both of these have one double bond present over here. Then next, IUPAC nomenclature is same. If you are going to name both of these compounds, it is going to come same, right? I am saying DU is same, IUPAC name is same, molecular formula is same, students, because it is an isomer. Now, what else is same over here? Connectivity is same over here. That means, see, this carbon is connected to CH3H. This carbon is connected to CH3H. If I consider individually, this is connected to CH3H. Here also it is connected to CH3H. Each atom is connected to CH3H, 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 but arrangements are different. Here both of the CH3 are present in the upward direction, but here what we see, one is present over here, another is present over here in a diagonal position, right? So the arrangement of atoms in space are different, rest all of the things are same. Here same connectivity is seen. Same connectivity of atom is seen. Now, students, if you remember structural isomer, I told you that there was a difference in structures, right? So there were different connectivity. Here is same connectivity. So you could now connect both of these structural and stereo, in which aspects they are different from each other, right? Now, students, moving to the classification of stereoisomers. When I classified isomerism, I just directly wrote about optical and geometrical. But if I have to classify into further categories, stereoisomerism can be classified into configurational and another one is conformational. Now, configurational is further classified into enantiomers and diastereomers. Enantiomers are further classified into erythreo. Here, erythreo will come. and here 3O will come. Here 3O is 3O, and diastereomers are further classified into optical and geometrical. So first of all, which we are going to study right now is going to be geometrical isomerism. Then we will move forward towards the optical. So once you get these terms, these are nothing in front of them, right? So first of all, I am going to start with the geometrical, but before them, let me classify stereoisomerism into configurational and conformational with a very beautiful example. Let us learn about configurational and conformational. So when I say students, basically two different compounds are seen, that is configurational. I am saying when two different compounds are seen, here two different compounds, that is referred to as, configurational. Don't get confused. This is just to, separate both of these. If I talk about conformational, I would say one compound but different forms. Here, I would say one compound but different forms. How I can say that? For example, if I say that God is only one, but I would say that, you follow a particular religion. So you follow their religion, God. So its forms are different, but God is only one. No. So that same applies over here in the conformational. Compound is one, but it is represented in different forms. Now, students, what is the basic difference in both of these? That if I want to convert, one configurational compound into another configurational compound, during the interconversion, bond cleavage is required. But if I talk about conformational, there is no need for the bond cleavage. With the help of rotation, it is possible. Don't get confused. I am going to take one example which will help you to determine what is configurational, what is conformational. So here what I am saying is that during interconversion, bond cleavage is required, or bond breaking. Cleavage refers to as bond breaking, right? And here no bond breaking required. With the help of rotation, you can do so, right? With the help of rotation, you can do the interconversion. Now, a trick to identify both of these is that if I talk about configuration, I would say two bonds, are fixed and the rest are to be broken. But if I talk about conformational, one bond is always fixed. Here, a trick to identify both of these, two bonds will be fixed and rest will be broken, right? This is a trick to identify. And here if I say one bond is fixed. Now what I meant by this term, let us see with the help of one structures. Now if I talk about the very first structure for the configurational compound, it is quite simple. Okay, if I take this case, this is the case for configurational. Why I am taking this case for configurational? I told you in configurational that bond breakage is required. Why bond breakage is required? See, if I want to convert this compound into this compound, what I need to do is I can see that both of the CLs are present over the upward position. But if I see this compound, one CL is present over here, another is here in the diagonal position. To convert this into this, I need to kindly break one of the bond. Like I have to break this bond with this bond, and I have to replace this bond with this bond. So I need a bond breakage over here. So here, to for interconversion, bond breakage is required. So here double bond is present. Due to this, we need to break the bond. Students, if single bond is present, no, it can easily rotate. But when there is double bond, there is a bond breakage. It is a restricted rotation. The bond cannot be rotated easily, So to convert this, we need bond breakage. Hence, it is referred to as configurational. Now, these are configurational. And there was a trick, I already told you two bonds will be fixed. So you can say, now these bonds are fixed. you have to, break other bonds. Clear? Now, if I take example of conformational students, this is my first, compound. If I'm taking example for conformational, okay. Now the trick to identify conformation, I told you one bond is going to be fixed. Here you see, this is carbon atom, you already know, right? Now here, if you see, here is OH, here is CH2H, it is not same. Here is H, here is OH, it is not same. Here is CH2, here is H, it is not same. But this bond, CHO bond is fixed. One bond is fixed, another ones, are not fixed. So again, one trick, here two bonds were fixed, here one bond is fixed. To convert this, what we can do is we can rotate it. We can just put a hand over here and rotate the another one by keeping one bond fixed. So it will be converted into OH, H will come down and CH2H will go that side. So these are conformationals. Now you can easily identify between configurational and conformational. I hope so. Now students, comes the very first topic that we need to do for the case of, this we have already done about configurational. Now moving forward towards the geometrical isomerism. As I told you, first we will classify into configurational, conformational. Then we are going to study in depth about geometrical and then towards the optical. So what do you mean by geometrical isomerism? First of all, geometrical isomerism, it arises due to arrangement of groups present in restricted rotation. What do I mean by restricted rotation? It is important thing for you to understand. See, if I say carbon-carbon single bond is present, if I say carbon-carbon single bond is present, and if I say carbon-carbon double bond is present, I say kindly rotate the system. So you can easily rotate over the single bond. Through the single bond, rotation is quite simple, but with the help of double bond, students, it is quite tough because bonds break. It is quite tough for double bonds case. Here it can rotate, but here it can't rotate. So the position at where our bonds can't rotate, they are referred to as restricted rotation. Here, where rotation is not possible, where rotation is not possible, students, is known as restricted rotation. Clear? Okay. Now let us see the cases where restricted rotation occurs. First case, I would say carbon-carbon double bond. This is the very first case because double bond is there. It can't be rotated. It will break. Second case is carbon-carbon triple bond. The third case, if I talk about, is carbon-nitrogen double bond. And over here, there is a lone pair of electrons and like this. So here again, you can see the double bond case arises, so it will break. Another one is carbon-oxygen double bond. Okay. Other than this, oxygen-oxygen double bond, then I would say nitrogen-nitrogen triple bond. These are the cases, students, where rotation is restricted. Then comes the case for the ring-like structure, if I would say. For example, this is a ring-like structure and I have to rotate it. It will break. It will break. So again, here rotation is restricted. Another case, if I would take, here also the bonds will break because when I am going to rotate it. Other than this, I can take one more example. Here also, where double bond in the ring inside it is present, it is a kind of restricted rotation. So these all are the cases of restricted rotation where we are going to see geometrical isomerism, right? Because for geometrical isomerism, we need restricted rotation. Now, what are the conditions for geometrical isomerism, students? Molecule must have at least one bond about which rotation is restricted. At least one bond should be present through which rotation can't be possible. ठीक है. इसके बाद स्टूडेंट्स देखो, सेकेंड इज ग्रुप्स प्रेजेंट ऑन बोथ टर्मिनल्स of bond about which rotation is restricted must be different. It is most important. What is written over here? Let me tell you. Groups present at both terminals. I am drawing with you carbon, carbon. A, B, C, D. Listen to me carefully. Groups present at both the terminals of the bond. This is the double bond. where the restricted rotation occurs because it is a double bond. Here restricted rotation is occurring, and the groups which are present over these terminals, over the terminals where the rotation is restricted, which rotation is restricted must be different. That means A cannot be equal to B, C cannot be equal to D. Individually you need to see, individually across the double bonds. Kindly see this carbon, it should contain different groups. Kindly consider this carbon, it should contain different groups, but these two can be same. A and C can be same, B and D can be same, but individually we need to see the groups should be different. These two should be different, these two should be different. You know, don't get confused that these should be different. No, individually you need to see. Now students, if I talk about the case for geometrical isomer, an example for geometrical isomer, for this case only I can make, for this case only, where I am saying that yes, they can be different. Let us say this is A, this is B, this is again A, this is again B. Another case, A, B, B. Now these both are geometrical isomers of each other. Why? Because orientation is different. How come? See, there is a restricted rotation over there because there is a double bond. Now groups should be different. Here is A, here is B. It's okay. Now check this, A, B. It's okay. It's right. A can be possible, B can be possible. Individually it should be different, individually it is. Now let us see this case, AB, it is different. So hence these are geometrical isomers of each other, students. Now let us see the very next thing, that is, in which of the following molecule geometrical isomerism is possible. Now you need to check out in which of the following is geometrical isomerism possible. So first condition that you need to keep in your mind is restricted rotation. Find out where is restricted rotation, then check that the double bond where the restricted rotation is there, or the ring where the restricted rotation is seen, the terminals should have different groups, right? So if I take the very first case here you can see here is a double bond. So where there is a double bond, there will be a restricted rotation. Okay, the next step was to check the different groups should be present over the terminals. If I talk about this terminal carbon, it has same hydrogen, it has HH, but as I told you, A cannot be equal to B, but here it is having same group, so here rotation is not, here geometrical isomerism is not seen. Now if I talk about this case, students, again here is one carbon, here is another carbon over the double bonds. Over the double bonds there are two carbons. Now we need to check different groups. Here if I see, one is hydrogen, another one is this big group, and if I talk about this carbon, two hydrogens are present which are same. So hence here no geometrical isomerism is possible. Okay, now let us see over the next case. If I talk about the B case, NH double bond NH, what do you observe here? This is the double bond where the restricted rotation is seen. Double bond is a case of restricted rotation. Now the next step is to check the different number of different groups on the terminals. Now here is nitrogen, which is the terminal, here is nitrogen, they should have different group. Nitrogen is having one hydrogen, another one is the lone pair. If I talk about this nitrogen, it is having one hydrogen, another one is the lone pair. So individually they have different groups, right? So hence here geometrical isomerism is possible. Okay, now let us see the next case, students. In the next case, I have CH3 single bond CH double bond NH. Now, here again double bond is present, so restricted rotation can be seen. Second step is to check where there is restricted rotation, the terminal groups should have different atoms. So if I talk about here, nitrogen is the terminal group and here carbon is the terminal group. Nitrogen is having one hydrogen, another one is the lone pair again. And if I talk about this carbon, it is having one hydrogen and another one is the CH3. So it is having different groups. Hence here also geometrical isomerism is possible. Clear? Okay, now let us see the next case. For the next case, it is CH3 single bond CH double bond CH single bond CH3. Now let us see, here double bond is present, so I would say here restricted rotation is seen. Now they should have different groups on the terminals. Now this carbon and this carbon are the terminals. It has one hydrogen and one CH3. It has one hydrogen and one CH3. So individually they have different groups. Hence geometrical isomerism is also possible over here. Now let us see this case. I told you, in ring case, it is a restricted rotation. So this carbon contains different groups while this contained. So I would say this is the ring where restricted rotation is seen. Now this carbon should have different groups. It has hydrogen, it has CH3, different groups. And this carbon is also having H and CH3. It is also a different group. So across these two carbons, yes, geometrical isomerism is seen. Clear? Now let us see the next case, students. Next comes the conditions for geometrical isomerism. In which case? In carbon-carbon system, in carbon-carbon double bond system. This we have already seen. The very first thing that should be the presence of carbon-carbon double bond for carbon-carbon double bond system. Presence of, first condition is presence of carbon-carbon double bond, right? The next thing, the terminals across carbon-carbon double bond should have different groups. Should have different groups, my dear students. Okay, they should have at least different groups. Now, if I talk in a pair of geometrical isomerism, distance between the similar group changes. Kindly write this down. In pair of GI, that means geometrical isomerism, distance between similar groups changes. Clear, students? Now let us see some cases where geometrical isomerism can be seen or cannot be seen. Okay, if I talk about CH2 double bond CH2, kindly tell me, is geometrical isomerism possible over here? So you will say that, ma'am, first condition is being followed, that yes, double bond is present, but the terminals should have different groups. But here carbon is having two same hydrogen, here also hydrogen hydrogen, hence geometrical isomerism is not possible over here. So if I take a next example, that is CH3 CH double bond CH2 over here, kindly tell me geometrical isomerism is possible or not. So you will say that, ma'am, double bond is present. Now we need to check the different groups, but this carbon is having one hydrogen and one CH3, but this carbon is having same hydrogen hydrogen, hence geometrical isomerism is not obtained over here because one terminal is having same groups, right? If I say one more example, CH3 CH double bond CH CH3. So over here I would say there is, yes ma'am, double bond is present over here. Next condition is that the carbons must have different terminals must have different groups. So hydrogen CH3 different, hydrogen CH3 different, hence here geometrical isomerism is possible. Now students, comes the most interesting topic, that is going to be stereogenic center. Now stereogenic center is that center basically through which we can see the geometrical isomerism. So that stereogenic center can be a double bond, it can be a ring, it can be a chiral center. So see, the double bond, the ring, the chiral center, due to which the stereoisomerism is caused or the geometrical isomerism is caused, is known as stereogenic center, students. Due to which you can see the geometrical isomerism. So that particular double bond or ring, or I would say chiral center, is your stereogenic center. Now let us see this case. How many stereogenic centers are present over here, or I would say identify the stereogenic center over here. So first of all, see this double bond. Yes, there is a double bond. Kindly check, is there any geometrical isomerism possible? If it is possible, then it is a stereogenic center. Okay, now here we have these carbons as our terminal groups. They should have different groups. It has hydrogen CH3, it has hydrogen CH2. So yes, geometrical isomerism is possible. Hence, through this double bond geometrical isomerism is being caused. So this is our stereogenic center. You can also put a star over here. So how many stereogenic centers? One stereogenic center. Clear? Now let us see the another case. In this case, I would say we have this double bond over here. So this double bond have two carbons over terminal position. Here is one hydrogen, one CH3, different groups. Here is one hydrogen and all of the group here. So these are different groups. Hence it is a stereogenic center because geometrical isomerism is possible over here. Now let us see this double bond. If I talk about this double bond, here is one hydrogen and CH3, different groups. Here is hydrogen and all of the other group. So here also geometrical isomerism is possible. Hence it is also a stereogenic center. So here basically there are two stereogenic centers and geometrical isomerism is also possible. Now let us see the next case. If I talk about this double bond, here I would say hydrogen and CH3 are the different groups. Here I would say hydrogen and this is a different group. So here it is referred to as a stereogenic center because geometrical isomerism is possible over here. But if I talk about this double bond, I would say here is hydrogen and the another group. And if I see here two hydrogens, same groups are present. So it can't show. It can't show. How many stereogenic centers? Only this. This can't show. This can show. Right? So geometrical isomerism is possible, but here stereogenic center is only one. So kindly put a star over here so that you can differentiate further. Clear? Okay. Now let us see over more cases. If I see We are students right now talking about carbon-carbon double bond. Right now, I'm not considering ring, so don't get confused that you will see ring also. I'm just talking about carbon-carbon double bond. So kindly check across that. Individually, first we will study in carbon-carbon double bond, then in ring, then we will study together also. Clear? So if I see across this double bond, I have CH3H, different groups. Now see how to check across this double bond over this side, left hand side. Move from this direction. What are you getting? You are getting carbon, again you are getting carbon. Now move in this direction. What are you getting? Carbon, again carbon. Same groups now. You are getting same groups in both of the sides. Hence, geometrical isomerism is not possible over here. So when geometrical isomerism is not possible, hence I would say there is no stereogenic center over here. Clear? Okay. Now let us see the next case. Again, this across this double bond, we have CH3 and H, we have CH3 and H, different groups. Now move in this direction, what are we getting? Carbon and two Cls are attached over here. But if I move in this direction, what I'm getting? Only carbon. So there are two different groups, right? So here geometrical isomerism is possible. Means this double bond is, yes, causing geometrical isomerism. Hence it is a stereogenic center. Clear? Now if I see this double bonds case, across this I am seeing CH3H, which are different groups. In this direction, what I am seeing, I am moving in this direction, I am getting carbon, chlorine, chlorine. If I am moving in this direction, I am getting carbon, bromine, bromine. Hence different groups. So I would say yes, it is a stereogenic center. Geometrical isomerism is possible over here. Now let us see towards the next case, students. In this case again, across the double bond, what I am seeing is hydrogen CH3. These are the different groups. Here I am seeing ET. ET refers to as ethyl. Ethyl is CH2CH3. See, in some of the cases you are going to see Me, that is CH3. ET, that is CH2CH3. Ethyl. So again, you are getting ET and you are getting CH2CH3. It is almost the same thing. Same thing. So same groups are present over here. So there is no geometrical isomerism. Hence there is no stereogenic center over here. So examiner makes you confuse over here. Right? So observe very carefully while you are solving any of the questions. Now comes the next question here. See, this is the double bond. Across this we need to check. So here this carbon contains hydrogen and this group, which are different. And if I talk about here, this hydrogen and these are the different groups. So yes, it is a stereogenic center. It is causing a geometrical isomerism. Now let us talk about this double bond. This double bond has this carbon and this carbon as a terminal. Now this carbon contains two same groups, hydrogen. So it can't show geometrical isomerism because it has same groups, right? Now let us see this double bond. If I talk about this double bond, it has hydrogen and CH3, which are different groups. And if I see here, it is hydrogen and this whole is different groups. So yes, it is also stereogenic center. So now how many stereogenic center I would put across with this color? Don't get confused over here, okay? Two stereogenic centers are there. This double bond is not showing any stereogenic center. It is not showing any geometrical isomerism. Clear? Okay. Now let us see the next topic, that is geometrical isomerism in ring. Now we have seen in double bond. Now comes the case of, ring. Now students, if I talk about ring again, here first thing I need to remember is restricted rotation system should be present. Second thing which I need to remember is at least it should have two sp3 members of the ring. That must be die substituted. At least two sp3 member of the ring should be die substituted. Should be die substituted. That means it should contain different groups. Each should have different groups. For example, let us take one case. Okay. Now this is my case. If I talk about this case, this is a ring, yes. Now let us check the carbons which are sp3 hybridized. If I talk about this carbon, 1 bond, 2 bond, 3 bond, 4 bond. Now 4 sigmas are made, that means it is sp3 hybridized. If I talk about this, it is also sp3 hybridized. Now if I talk about this carbon, it is also sp3 hybridized because these two bonds and two bonds with hydrogen. But necessity condition, it should be die substituted. It should have different groups. Here you can see A group, B group, these are different. If I see this carbon, C group, D group, it is different. But if I see this, it has hydrogen, hydrogen. So here across which I could see geometrical isomerism? Across this bond. because across these two carbons, because they have been disubstituted. They are sp3 hybridized and they have different groups. That's why. Not with this one, because it have same group hydrogen and hydrogen. Now students, let us see in the rings cases where it is possible and where it is not. So here again it is sp3 hybridized, it is also, but here two hydrogens are present, so we are not considering it. We will consider this and this. I see here CH3 which is same group, which can't be same, it should be different. So here again geometrical isomerism is not possible. If I see this case, this is sp3, this is sp3, this is sp3, it is disubstituted, but these contain hydrogen only. So here also geometrical isomerism is not possible. At least you should have two carbon atoms which are sp3 hybridized, which are disubstituted. Here only one is sp3 hybridized, which is disubstituted. Others are sp2, but they are not disubstituted. Clear? Okay. Now let us see this case. If I see here, it is sp3 hybridized, it is disubstituted. You will say, how, ma'am? See, one is CH3 group, another is hydrogen. One is CH3, another one is hydrogen. You have to consider individually. So individually it has hydrogen CH3, it has individually hydrogen CH3. So yes, here geometrical isomerism is possible. Clear, students? Now let us see more cases over here. Now see this case again. This contains methyl, one hydrogen. This contains methyl, one hydrogen. So here also it is possible. Clear? Now let us see this case. Here I want you to consider all of the cases. Double bond, rings, everything. So if I see this double bond, is geometrical isomerism seen over here? So you will say, ma'am, these two are the terminals. It contain hydrogen CH3, different groups. It contain hydrogen and this, it is different. So here it is a stereogenic center. Yes, it is a stereogenic center. If I talk about this ring-like structure, students, see, it is sp3 hybridized. It has this group, it has hydrogen. It has sp3, it has this group, and it has hydrogen, which are different. So yes, it is also stereogenic center. This ring acts like a stereogenic center now here. Now if I talk about this double bond, it has hydrogen and this group like structure, which is different. If I talk about this, it has hydrogen and this group like structure, which is different. So it has basically three stereogenic centers over here, students. So it shows geometrical isomerism. Now, so students, as we have already seen the case of double bond ring individually, now we are going to see geometrical isomerism in which double bond is present inside the ring. Now for this case, I would say that if you want to see geometrical isomerism for the case when double bond is present inside the ring, then only 8-membered or more than 8-member are the valids which will show geometrical isomerism. But for the small size one, students, they won't show geometrical isomerism because the trans isomer in those cases is unstable, due to which geometrical isomerism is not possible. So kindly write these things, that for 8-membered or above, geometrical isomerism, geometrical isomers are observed in the case of double bond inside the ring, of double bond inside the ring. For small size geometrical isomerism is not seen as trans isomer is unstable. Now students, kindly write few more points. For 8-membered, 9-membered, 10-membered, cis form is stable. Cis form is stable. But for 11-membered, trans form is stable. In the coming topic, when we will do the nomenclature for the geometrical isomer, we will get to know about cis form and trans form, so don't get confused. Okay. Now students, I'll show you one of the examples over here. Now, this is the example for 8-membered compound where we can observe geometrical isomerism. So now let us proceed towards our next topic, that is going to be oximes. Students, if I talk about oximes, what are oximes? When we treat carbonyl compound with ammonia derivative and the derivative is taken as OH group, then oximes are obtained. Now let us write this reaction. I am talking that we will take a carbonyl compound. Now carbonyl compound is the one in which carbon double bond oxygen is present, right? Now it can be aldehyde, it can be ketones. So R group, and over here it can be H or R dash. If here H will be present, then it is referred to as aldehyde. If R dash is present, then it will be referred to as ketonic group. So we will react it with ammonia derivative. Here G is, if you take G as OH, then only you will get oxime, right? So what do you observe over here? That water gets liberated out, and what do we get? We get CR H R dash. According to aldehyde or ketone, it will be seen. Then comes your double bond nitrogen and then the G group, right? Now here I told you, if you take the G group as OH, then it is known as oxime. How do it looks like? Let us see this. Carbon R H or R dash, nitrogen lone pair OH. This is the structure for oxime. Now the question which arises in examination is that they will give you different alkyl groups over here. You need to see first of all that if double bond is present, then yes, it is restricted rotation system. The second most condition is that the terminals should contain different carbon atoms, different groups, not carbon atom, different groups. So if they contain different groups, then geometrical isomerism is seen there, right? Now we will move forward towards our next case, that is known as cumulines, students. If I talk about cumulines, basically what are cumulines? Hydrocarbons containing adjacent pi bonds are cumulines. So these are hydrocarbons containing adjacent pi bonds. Now students, we divide cumulines into two basic categories. One is even cumuline, another one is odd cumuline. Even and odd, depending upon the number of pi bonds. Clear? If the number of pi bonds come out to be an even number, then it is referred to as even cumuline. If the number come out to be odd, then it is referred to as odd cumuline. Let us take an example of allene, the most famous even cumuline, allene. Now what happened in this case? Two pi bonds are observed over here. Now students, if I draw its structure according to the chemical bonding to find out whether it shows geometrical isomerism or not, first of all I need to know what is the hybridization of the carbon atoms over here. So if I see this first carbon atoms, it is sp2 hybridized because it contains 3 sigma bonds. If I talk about the centralmost carbon atom, it has 2 sigma bonds, hence it has sp hybridization. And if I talk about this carbon which is on the terminal position, it contains 3 sigma bonds, which is referred to as sp2 hybridization. So if I draw according to the chemical bonding, what do I observe over here? Kindly see this. First of all, I'm making single bonds between the carbon atoms. Now I know that these are the p orbitals, that are involved in making bonds. One by one, I'm going to tell you what I have done over here. Okay, now students, basically this is your structure which I have drawn you above. I will explain you right now. See, this is actually, it looks like this. How? See, if I talk about these two carbon atoms, single bond is the sigma bond. While I talk about pi bonding, these are the p orbitals that are involved in pi bonding. As you know, this lie in this plane, so this hydrogen is towards the observer. That means you are the observer, you are looking at it, so this hydrogen is towards you. While this, dash hydrogen is away from you, at the back side of the observer. So it is towards the observer, it is away from the observer, right? Why? Because these are in the plane, so they are towards and the back. Now when these are, not in the plane, hence this hydrogen comes in the plane. So now what do we observe here? We observe that both of the terminal carbons, this carbon atom, if I talk about, and I talk about this carbon atom, these are out of the plane. and hence it is out of the plane. What do we see here? What do we see here? We see that students, while drawing the structure, while drawing these structures, basic structures, if I say here CH3 is present, here H is present, if I draw it in such a way, what we see according to the structure, what actually happens, this is for example distance L1 and this is for example the distance L2. What happens over here? L1 is equal to L2. How, students? Because these both carbons which are present at the terminals are out of the plane, hence the distance between these are equal. Distance, now as I told you in the geometrical isomerism during the starting, that the distance of the similar groups should remain, they should remain different. L1 should not be equal to L2, then it is referred to as geometrical isomer, but here L1 basically is equal to L2, so here it will not exhibit geometrical isomer, students. Is it clear to you how I can say that L1 is equals to L2? Because students, when you see if you are seeing through the board, you will say, ma'am, this distance is short while this is long, but it is not actually the truth. Why? Because we can see this in 3D imagination. While these hydrogens are present like this, the terminals one, if I talk about this hydrogen, it is present in front and another one is present at the back, so here the distance becomes equal. But if I talk about the odd cumulants case, students, what happens? Now let us see that also. In the case of odd cumulants, what do we observe? For example, carbon, double bond carbon, double bond carbon, double bond carbon. Now here 3 pi bonds are present, right, students? So what do we observe over here? To make its structure more clear to you, through chemical bonding, first of all, we are going to show the single bonds. Now, its p orbital is involved like this. It's just for your explanation I am drawing. No need to draw. Just understand by sitting that what I am doing over here. Okay, students, now let us see what happens over here. In the previous case, what do we observe? The terminal carbons had different hydrogen. One had in the plane, another had towards the observer and behind the observer. But in this case, what happened? We saw that these two terminal carbon atoms, what is seen over here? That they are, they are in plane. They were out of the plane, now they are in plane, they are equal. When they are in plane, what do we observe? We observe that, for example, this is the case. For example, this is the case. This is your L2 distance. This is your L1 distance. Now, L1 is not equal to L2. Hence, geometrical isomerism is possible over here. Okay. So now you need to understand. Kindly keep in mind that odd cumulants will show geometrical isomerism, while even cumulants won't show geometrical isomerism. Kindly write it down. Till then, I will have water. Okay, students. Moving forward, let us see some of the examples and let us check out, does it show geometrical isomerism or not. In this example, now you have to consider it one stereogenic center because it is a case of cumulin, right? Now let us check, it is a case of even cumulin or odd cumulin. How many pi bonds? 1, 2, 3. It is for odd cumulins now. Okay, it's for odd, it can show, but we need to check that the terminal carbons should have different groups for them to exhibit geometrical isomerism. So here similar groups are present, hence this will not exhibit geometrical isomerism. Clear? Okay, now let us see this case. If I talk about this case, what do we observe here? here this double bond is present. So it has these two terminal carbons over here. If I talk about this carbon, it is having hydrogen and CH3 groups, which are different. Hence it is a stereogenic center because it will show geometrical isomerism, because here also hydrogen and another group is present. So this has the terminal carbons which have different groups, right? Now if I see this case, students, these are the adjacent pi bonds. That means this is the case for cumulins. So here how many pi bonds? 1, 2, 3. Again, that means it's for odd case. Now what we need to check? We need to check that here different groups should be present on the terminal carbons. This carbon have hydrogen and CH3, so different groups. This carbon has hydrogen and other groups. So yes, this will also exhibit geometrical isomerism, and hence it is also one of the stereogenic center. Hopefully it is clear to you, students. Now let us move forward towards spirenes. Students, basically spirenes are consecutive cyclic parts which are joined with each other. Now what do you mean by that? Let us see. Okay, basically this is the structure for spirene, students. When you see that cyclic paths are joined with each other, these are spirenes. Now for the case of spirenes also, these are of two kinds. One is the odd one, another one is the even one. Again, when you are going to draw all of these structures, what you are going to see here, that even spirenes, will not show geometrical isomerism. They will not show geometrical isomerism, while odd one will exhibit geometrical isomerism. I will give you one of the example of odd spirenes, so that you get to know how it is correlated with cumulins. Just similar to that, here also we need to find out in plane, out plane. We need to mention wedge dash projections. That's it. So now let us see how. If I talk about the system, I would say this is hydrogen, this is hydrogen. I am taking about this carbon atom. Okay, now if I talk about this carbon atom, with the red pen only we'll move on. See, this is away from the observer, this is towards the observer. Which bond I'm talking about? I'm talking about this bond. This bond, I'm talking about this bond. Now what happens is, now the other carbon that is making the bond with it will also be away from the observer. Another one is towards the observer in such a way. Hence the other two will be in plane. So the other two will be in plane. Now these are in plane, right? Now the next one is also going to make in plane. It is also going to make in plane. Now the next one is going to be away from the observer and towards the observer. Clear? Now let us see. We have made this. Now the next one, students, what it is going to do? It is going to again, go away from the observer, hence towards the observer. So the hydrogen that are left over here comes in plane, right? Now what do you observe here? That the terminal carbon atoms, this carbon atom and this carbon atom, now have the hydrogen in planes, right? So here again in planes arises. When in plane arises, what do we observe? We observe that L1 is not equal to L2. Hence geometrical isomerism is observed. While if I talk about the even cases, this is not at all seen in that. So you need to remember, even cumulins or even spirenes won't show geometrical isomerism. Odd cumulins and odd spirenes will show geometrical isomerism. So this was all about spirenes, students. Let us see a few examples over here. Like first of all, we need to check how many rings are present over here. So 2 rings, that means it is even spirene, so it is wrong. It can't show geometrical isomerism. Now if I see this structure, yes, it has 3 adjacent rings, so yes, it is odd case of spirene, it can. Now the terminal carbon should have different groups. Here Br, Cl, different groups. Here also Cl and Br, different groups. Individually we want to see, so yes, it will exhibit geometrical isomerism. Now students, we are coming towards our important topic of today's lecture, that is calculation of geometrical isomers. Kindly put a star over here because it is the most important topic, and yes, question can arise from this. Now students, to calculate geometrical isomers, we have 3 basic cases. One is for dissimilar ends and the other 2 are for the similar ends. What I am talking is, let us write down. We need to see 3 basic cases. Number first is when dissimilar ends are present. When dissimilar ends are present. Okay. Other one is when similar ends are present. And in similar ends when n is equals to even, while in similar ends only when n is equals to odd. Now, what do you mean by similar ends or dissimilar ends? I will tell you in the upcoming cases. First of all, we need to write the formulas for the following. For the dissimilar ends, I would say number of geometrical isomers is equal to 2 raised to the power n. This is the basic formula that you need to keep in the mind for the dissimilar cases. Now, if I talk about the similar cases when n is equals to even, students, I would say geometrical isomers is equal to 2 raised to the power what? 2 raised to the power n minus 1. Now keep in your mind n minus 1. Here also when you will write, it will be 2 raised to the power n minus 1. Now the next step is going to be quite different. The next step is that you need to add something. So again positive sign will come for both of the cases. Now comes the twist. Here again write 2 for both of the cases. In the very first case, what you are going to see, n by 2 minus 1, and for the next case you will see n minus 1 by 2. Here is n by 2 minus 1 and here is combined n minus 1 by 2. Now these are the formulas when you see n is equals to even, and for the another one you are going to see when n is equals to odd one for the similar ends. Now I will tell you where to apply which situation. Let us see for the very first case. In these cases, what you need to see, students, see, take left hand side and right hand side and start moving from outwards toward the inward side. Check the groups. If they are similar, then these are the similar ends. If they are different, then that is the dissimilar ends. So if I see from this side CH3 is there, from this side also CH3 is there. Now I will move inward. Here CH is there, but here CH2 is there. That means different, groups are present. Further, here double bond is there, here single bond is there. That means it is the case of dissimilar ends. It is the case of dissimilar ends. Now for dissimilar ends, what was the formula for geometrical isomers? So number of geometrical isomers for dissimilar ends is equal to 2 raised to the power n. Now what here n refers to? N refers to as stereogenic centers that are responsible for geometrical isomers. Now let us check here. If I am going to check this double bond, this has this carbon and this carbon. It has hydrogen and CH3, the different groups. Here hydrogen and another the different groups. Hence this is a stereogenic center which is responsible for geometrical isomerism. So if I talk about this double bond, again it has 2 carbons, it has hydrogen and the other group, it has hydrogen and the other group. So it is also a geometrical, it will also exhibit geometrical isomers. So how many stereogenic center? Total 2. So here n is equals to 2 raised to the power 2, that means 4. So number of geometrical isomers here that we'll be getting is 4. Now let us see the next case over here. Again, let us find out if it is similar end or dissimilar end. So here it is CH3 group, while here it is C2H5 group. That means it is dissimilar end because dissimilar groups are present. So again, it is the case of dissimilar ends. Now for dissimilar ends, what we need to do? We need to do simply 2 raised to the power 2. Sorry, 2 raised to the power n. N refers to as stereogenic center. Now let us see over here. If I talk about this double bond, these are the carbons. It has hydrogen CH3 different group. It has hydrogen and the another group. So here it is a stereogenic center. Now if I talk about this double bond, here also carbon, these are the terminal ones. It has hydrogen, it has C2H5 different groups. It has hydrogen, it has different groups. Again, like the previous case also, n was equal to 2. Here also n is also equal to 2 again. So here 2 raised to the power 2 comes out to be 4. So in the second answer also, your answer comes out to be what? 4. Now let us see the next case. For this case, first of all, we need to find out it is dissimilar end or similar end case. So here CH3 is present, here CH3 is there. Here CH, 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 CH. From moving outward towards inward, we get the same situations, right? So this is the case of similar ends. Very sorry. Yes, students. Now, for the similar ends, we need to find whether n is equals to even or odd. First of all, we need to check out. So let us see over here. If I talk about this double bond, it has these two carbons. This carbon has hydrogen and CH3, which are different groups. And if I talk about this carbon, it has hydrogen and this is the different group. So yes, it is a stereogenic center. If I talk about this double bond, so it has these two terminal carbons. It has hydrogen and CH3, which are different group. And if I talk about this carbon, it has hydrogen in this group. So these are different groups. Again, here n is equals to 2. Now, here n is equals to 2, but here it is similar ends. Now, for similar ends, student, what was the formula? Number of geometrical isomerism or geometrical isomers is equals to 2 raised to the power n minus 1. It was different from the dissimilar one, so don't get confused. Now comes plus 2 raised to the power n by 2 minus 1. It was the case for what? It was the case for the even one, right? Now we are going to write n value as 2, 2 minus 1 plus 2, 2 by 2 minus 1. Now 2 raised to the power 2 minus 1 is 1 plus 2 raised to the power 2 by 2 is 1 minus 1. 2 raised to the power 1 is 2 plus 2 raised to the power 1 minus 1 is 0. Now something raised to the power 0 is equals to 1. Don't get confused. It is the maths that you need to keep in your mind. When there is given a number and it has a power 0, it is referred to as 1. So here 2 plus 1 is equals to 3. So answer will come out to be 3. Okay. Now let us see the next case. I want you all to solve this first, then I will solve with you together. Okay. Let us see first of all. Let us check this is dissimilar or similar. Then we will find the stereogenic center. CH3, CH3, CH, CH, double bond CH, double bond CH, 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 CH. Similar ends. Clear? Now let us see the stereogenic centers. So here, these are the terminal carbons. It has hydrogen CH3 different groups. It has hydrogen different groups. It is a stereogenic center. Now if I talk about this double bond, here two terminals are there, hydrogen and another group, hydrogen and another group, stereogenic center. If I talk about this, it is also a stereogenic center and this one is also a stereogenic center. So how many stereogenic centers? It comes out to be 4, my dear students. Right? Now this is the case for what? This is the case for similar ends and the number comes out to be even. So what is the formula we have just done right now? Number of geometrical isomers is equals to 2 raised to the power n minus 1 plus 2 raised to the power n by 2 minus 1. Now n value is equals to 4. So 4 minus 1 plus 2 raised to the power 4 by 2 minus 1. So 2 raised to the power 4 minus 1 is 3 plus 2 raised to the power 4 by 2 is 2 minus 1. Now, 2 raised to the power 3 refers to at 8, 2 into 2 into 2, right? So, that is 8. 8 plus 2 raised to the power 2 minus 1 is 1. So, 8 plus 2, that comes out to be 10. So, here how many geometrical isomers will be formed? 10, my dear students. Now, let us see the next case. Here, first of all, check if it is of dissimilar or similar. So, there CH2 is given, here CH3 is given. So, that means it is dissimilar end because they are different. It is dissimilar ends. Now for dissimilar ends, it is the basic formula 2 raised to the power n, right? Now let us find the value for n. If we start from this side, students, this carbon is the terminal one. This has 2 hydrogen. That means same groups. Hence, it will not show geometrical isomer. Clear? Now, if I see about this double bond here, these are the terminal groups. It has hydrogen on the different group. It has hydrogen on the different group. Yes, it is a stereogenic center. Now comes this case. When, adjacent pi bonds are present, that means cumulants case, right? So, we will consider it single stereogenic center. Let us count how many pi bonds? 3. Odd case, yes. So, it will exhibit geometrical isomerism. How many stereogenic center? 1 cumulant and 1 this double one. That means 2. Here n value comes out to be 2. So, what is the number of geometrical isomers over here? 2 raised to the power 2. That comes out to be 4. Hope so it is clear to you. Okay. Now comes a quite different case for you people. Let us see. First of all, we will see if it is a dissimilar or similar. So it is but obvious that it is dissimilar. Why it is dissimilar? Because if you start from this side and if you start from the another side, they are different number of carbon atoms, right? So here, if I talk about this double bond, this is the carbon, this is the carbon. It has here methyl group, this is methyl and 1 hydrogen. If I talk about this, this has this group and 1 hydrogen. So different groups, yes, it is a stereogenic center, right? Now, if I talk about the ring and the double bond, see, two situation arises. Firstly, you need to see individually the ring, and then you need to see the double bond inside the ring, as I told you. See individually, then combine. So if I see individually this ring, I at least need, two sp3 hybridized carbon atoms. So that's not possible because only one is present over here. So single ring will not show geometrical isomer, but the double bond present inside the ring, can it exhibit? So for that to exhibit, what we need to see? We need to see 8-membered ring, right? Let us count from starting from here. 1 2 3 4 5 6 7 8. Yes, it is 8-membered. So yes, the double bond inside this ring will exhibit geometrical isomer. So one is there and one is there. That means n value is equals to 2. And as it is dissimilar case, so I would say that geometrical isomers here is equals to 2 raised to the power n. That means 2 raised to the power 2. That means 4. So the answer comes out to be 4. Clear? Okay. Now let us see the next case. I hope so that I've brought so many questions for you to practice. Now you won't, get it wrong in the examination. Clear? Because it is the most important topic in this chapter. Now, if I see this case, here is the double bond. These has these two terminal carbons. Now it has hydrogen CH3, which are different groups. It has hydrogen on this group, which are different. So it is a stereogenic center. Now if I talk about this double bond also, same over here, hydrogen and different group, hydrogen and different group. It is also a stereogenic center. Now for the ring case, find individual, then combined. If I see individual, yes, it is sp3 hybridized. Yes, it is sp3 hybridized. This group and hydrogen is present. This group and hydrogen is present. So yes, the ring will show geometrical isomerism. Now let us see the double bond present inside the ring will show or not. So that it will show when it is 8-membered or above that. Let us count 1 2 3 4 5 6 7 8. Yes, so it will also show how many stereogenic centers. 1 2 3 4. Now n value comes out to be 4. Check out it is similar or dissimilar. So it is dissimilar ends, right? So I would say number of geometrical isomers comes out to be 2 raised to the power n. That means 2 raised to the power 4. Now students, 2 raised to the power 4, that means 2 into 2 into 2 into 2. 2 into 2 is 4, 4 into 2 is 8, 8 into 2 is again 16. So how many geometrical isomers will be obtained? Total 16 will be obtained. Now let us see one more case over here. First of all, check if it is dissimilar, similar. So I will start from this direction and from this direction, because you can open this compound in such a way, right? So here this is present in between them. So don't start from this direction, right? CH3, CH, CH3, CH, CH, C, CH2. It is the case for similar ones. Now for the similar ones, we need to find out what geometrical stereogenic center, right? Now to check stereogenic center, let us see this double bond. It has carbon, carbon. This carbon has hydrogen CH3. This carbon has hydrogen on this group. So yes, it is a stereogenic center. Similarly, it also has a stereogenic center. Now if I talk about this double bond, this carbon has similar groups. So this will not show. How many stereogenic centers? 2 stereogenic centers. If n value comes out to be 2, that means that for the even case, now for the even case, we have a formula. Number of geometrical isomers is equals to 2 raised to the power n minus 1 plus 2 raised to the power n by 2 minus 1. Now, 2 raised to the power n comes out to be 2 minus 1 plus 2 raised to the power 2 by 2 minus 1. This comes out to be 2 raised to the power 1 plus 2 raised to the power 1 minus 1. This means 2 plus to the power 0, 2 plus 1, that comes out to be 3. Hence, number of geometrical isomers comes out to be 3. Okay. Now, let us see this case, students. Okay. This case is your homework. This case is your homework. I want in the comment section your answer with your name, students. Okay. So, it will be easy for you to understand. And yes, let us move towards the next one, that is the physical properties. Kindly mention with your name and your answer that how many geometrical isomers are obtained. So one case is for you, right? Now comes physical properties of geometrical isomers. This is a kind of interesting also and easy also topic. If I talk about physical properties, basically 5 physical properties are observed. One is the dipole moment, another one is the boiling point, third one is the solubility, fourth is the melting point, and fifth is the stability, students. So if I talk one by one, each of them, first comes out to be your dipole moment. Now if I talk about dipole moment, let us start from the very first. Okay, I'll write it over here. Okay, if I talk about the very first, that is dipole moment. It is represented by mu, students. It is represented by mu. Now, what is dipole moment? What is the formula for dipole moment? It is mu is equals to q, charge into distance. This is the very basic formula. Now, in general, cis isomer has higher dipole moment than trans one. It is in general. In general, cis isomer has more dipole moment than the trans one. Than the trans one. Let us make the structures also for you to easily understand. If I take this case, okay, now if I take this case, let us see over here. In this structure, what do we observe, students? We observe that dipole moment's direction is towards the electronegative atom in like this. Okay, here if I see, okay, so if I want a net dipole moment, it will come out to be like this. These both will add on, right? So here the net dipole moment is not equal to 0, but in this case they cancel out each other, so net dipole moment is 0. That means this is the case of cis. When both of the atoms are present on the same sides, then both of the atoms are present on the different side. That's the case of trans. So I would say here the net dipole moment comes out to be 0 because it is cancelling out, but here, students, it comes out to be something positive value, right? So due to this, it is polar in nature. Poles are created, positive, negative, hence it has more dipole moment in general as compared to what? Trans one. Now we will see our next category, that is our boiling point. If I talk about boiling point, then boiling point is directly proportional to intermolecular forces, which is further directly proportional to polar nature. So the second property I would say is boiling point. Boiling point. Now, as I told you, boiling point is directly proportional to intermolecular forces. Intermolecular forces, which is further directly proportional to the polar nature. Now, as I told you, in the cis case, dipole moment is added, hence polar nature is observed. That means the boiling point of whose will be high? Of obviously cis, because it creates a polar nature. Now, in the case of trans, there was no net dipole moment. That comes out to be 0, hence that was non-polar nature. So, as you know, boiling point is directly proportional to polar nature, hence we can say that boiling point of cis is more than of trans. Okay, kindly put this in a box for you to understand. Now let us see the next property, students. If we have seen the property of boiling point, now we will see the property of melting point. Melting point basically depends upon the packing. Okay, if I talk about the third physical property, that is melting point. Now, as I told you, melting point depends upon packing. As it depends upon packing, so if I take an example, now students, if you see, these groups are present in such a way that curved shape structure is obtained. Here a linear shaped structure is obtained. Here a curved shape structure you will see in cis case. Here you will see a linear shape. So linear shape has more packing as compared to the curved shape. Here packing is easy also and is good. Packing efficiency is also more as compared to our cis structure. So all I would say that the melting point basically is more of trans than comparative to cis, but boiling point of cis is more than of trans. So here melting point order is quite different from the previous case. Here of trans it is more. Clear, students? Now let us see our next property, that is solubility, students. What is the next property? Solubility. For the case of solubility, I would say solubility is inversely proportional to intermolecular forces. So the next property says solubility. Solubility is basically inversely proportional to intermolecular forces. Now, as you all know, cis has a very nice intermolecular force due to which it has a polar nature. So now its solubility will be less as compared to trans. Hence, I would say the solubility of trans is more than that of cis, right, students? So last point comes out to be stability, and stability of trans is more than of cis. So students, these were the physical properties that we need to, learn for the cases. Now comes the nomenclature in geometrical isomerism. Now basically nomenclature is of three kinds if I talk about. Number first is cis trans naming or nomenclature. The second one is EZ nomenclature. And the last one, students, is syn anti naming. So basically, we can name the geometrical isomers into three basic kinds. Number one is cis trans naming, number second is EZ nomenclature, and number third is syn anti. So first of all, we are going to study about cis trans naming. If I talk about cis trans naming, in which of the following cases these kinds are observed? So let us take a general example. If I say this group is A, this is B, this is C, this is D, right? So here A should not be equal to B, C should not be equal to D. This is the basic case over here. But students, kindly listen to me. A can be equal to C and B can be equal to D. So for this case, cis and trans nomenclature is applied. Now let us make one structure for you to understand. If I say this case, one second. Okay. If this is first compound, this is second compound, kindly identify which of the following is cis and which of the following trans. Cis means sisters, that means the similar groups will be present on the same side, and trans means opposite, that means they will be present on the opposite directions. So if I see in this case, I would say that Cl or Cl are present over the same side, that means these are cis, it is cis, and this is trans. And yes, it satisfies this condition also that these two are not equal to each other, but yes, they can be equal like this. Clear? Individually they should not be equal, but yes, opposite they can be equal. So I can take one more case over here. Sometimes you see the structure in such a way, so don't get confused. It is just the same. It is just the same. So here Cl and Cl are present over this direction. So this is cis and this is referred to as trans because Cl and Cl are present over the opposite direction. Clear? So this was cis trans naming. It was quite simple. But let us take one more case over here for you to understand it. Okay. Now, this is the case when you see students, it is not actually the same case. Why? Because here both of the hydrogens are present like this. But in this case, one hydrogen is, in this case, one hydrogen is present like this, another one is present inside. So here you see both of the hydrogen in the same side, that means this is the cis structure. Here one hydrogen is present outside while one is present inside, so this is the trans structure. So you can observe cis and trans in such a kind. Now comes the most important part of the nomenclature, that is EZ naming. Now what are the rules? One by one I'm going to tell you. In geometrical isomerism, E isomer is whose having a higher priority atom or group are at larger distance, and if higher priority group is at lower distance, then it is Z isomer. I will explain you by the following example. First of all, you all would be thinking that why is the need for EZ nomenclature? We have already done cis trans naming. So why is the need? Why is the requirement for this? Now let us see that general case which we have seen in cis and trans. We took this case, right? A, B, C, D. I told you A can't be equal to B, C can't be equal to D. But I told you A can be equal to C, B can be equal to D. So when this case arises, when A can be equal to C, B can be equal to D, then it is cis and trans. But when it arises that A also cannot be equal to C and B also cannot be equal to D, that means there are 4 different groups present. So in that case, E and Z nomenclature is applied. In that case, we apply E and Z nomenclature. For example, in this case, kindly tell me, is it a cis structure or a trans structure? So you would say, I don't know, ma'am, because if I see this structure very clearly, then 4 of the groups are different. At least one group should be there with the respect of which we can define cis and trans, but here all of the 4 groups are different. Hence, we need to require the naming EZ naming, right, students? Now let us see. Okay, let us see the CIP rule. What does CIP rule tells us? It tells us how to do the nomenclature of E and Z. You know, which is E, which is Z. The first rule says that atom will have higher priority order in which atom has higher atomic number. So according to the atomic number, you will give number. The atom who has higher atomic number will be preferred to as 1. The atom which has lower atomic number will be preferred to as 2. Okay, other than this, students, for isotopes, kindly write, for isotopes, you have to see its atomic mass. You have to see its weight. Heavier the isotope, you will give the priority to them. So for the case of hydrogen isotopes, tritium, then deuterium, then protium. Okay. And for the case of carbon isotopes also, carbon 14 is preferred, then carbon 12. Okay, so they will be given like tritium will be given the first priority number because it is the one that has the heavier isotope, that is the heavier isotope, right? Other than this, you have to see the atomic number. Whose atomic number is highest will be given the first number, whose atomic number is lowest will be given the second number. Now comes the second rule. In case of same atomic number, now for the case when there is same atomic number, kindly go and check the second atom. Okay, if the second atom has the same atomic number, kindly go and check the third atom. If third atom has the atomic number same, kindly go and check the fourth atom, and so on, my dear students. Now let us take one example and check it out. Okay, if I say I have this case with me. Okay, now for this case, kindly tell me which of the nomenclature is this. So first of all, we have this restricted rotation over here. Now the next thing that comes in our mind, it is fluorine, chlorine, bromine, iodine. That means iodine has atomic number more and bromine has atomic number less. If I talk about here, fluorine has atomic number less and chlorine has more. So students, for this case, what we see, 1 and 1 are present on the same side. That means when numbers are present on the same side, that is Z nomenclature. If we say someone best friends are basically refers to as jigri in Hindi, jigri dost. Oh, so from that jigri, I have just derived that Z is when they are present on the same side. And if I take another example, for example, if I am going to take, let us see, take a chlorine and bromine on one side now, and iodine and fluorine on the another side. Let us take this case for now. For this case, I would do what I would do again, fluorine, chlorine, bromine, iodine. So I would say bromine has more atomic number as compared to chlorine and iodine has more as compared to fluorine. So here 1 and 1 are present on the diagonal. That means they are the enemies now. For enemies, E nomenclature will come. So I have taken both of the cases where Z nomenclature will come and where E nomenclature will come, right? Now let us see the third rule. In order to decide the priority order, multiple bond is treated as hypothetically sigma bonds. Now here, multiple bond will be treated as a single bond. How? Let us take an example and I will tell you. For example, if I say there is given to you CH2 double bond, like this. First of all, I'm just explaining how you have to see this. Kindly write this. Like for example, this carbon has 2 hydrogen. first make a single bond with this CH. Now you know that it is making a double bond with this C. So it is making a double bond. So write separately, it is making a bond with C. Now you know this C is also making a bond with this carbon. So this C is also making a bond. So this is actually how you look to them. Okay, now when we will apply in the questions, you will get to know more easily. Now let us make one structure and find out how it looks like. So on one end, I would take hydrogen, carbon, deuterium here. Now here I will take a CH, double bond CH to the same case. And here let us take something different. Let us take a triple bond case. For example, I say carbon triple bond CH. Now let us find out here. If I talk about the isotopes, I told you deuterium will have atomic number more now because of the heavier isotope. It will be referred to as less. Now if I see, I have already opened it up like this. This is the main carbon, this is the main carbon through which it is attached, right? And if I open up this one, if I open up carbon, first of all, I will write single bond CH. Now it is, again, it has 2 pi bonds with this C. So it will be written 2 times bond with C. Now this C is also making 2 times bond with C. This C is also making 2 times bond with C, right? So I was talking about this carbon atom right now here. And here I was talking about this carbon. Now what we need to do is check the first atom. In both of the cases, the first atom is the carbon, this carbon, this carbon. Check the second atom. Second atom here is hydrogen, carbon and carbon. And in this case, it is carbon, carbon and carbon. It is further attached to carbon, carbon, carbon. It is secondly attached to hydrogen, carbon, carbon. So which has atomic number more? Obviously this. So it will be referred to as 1 number. It will be referred to as 2 number. And 1, 1 are present on the same side. That means they are the best friends. That means Z nomenclature. Clear, students? Like this you can apply on certain cases. Now let us see the last rule over here. The atomic number of lone pair is taken as 0. Therefore lone pair is always the junior group. So when you will see the lone pair in any of the cases, you will consider it as a 0. Okay, and it will be considered as a junior group. Now students, moving on to the next naming, we will see the cases of EZ in the coming questions. First, I want to explain all the namings to you. So now comes syn anti-naming. Now for syn anti-naming, we are going to see basically 3 cases. 2 for the oximes and 1 for the azoalkanes. For the oximes, basically there are 2 cases, aldooxime and ketooxime. Oxime are further as aldooxime and ketooxime. Now again, aldooxymes are the one where aldehyde group was obtained and ketooxymes are the one in which keto groups are seen. So now let us find out. If I see for aldooxime, students, what do I observe? I observe basically here what happens. This is my very first case. Here I will see hydrogen with respect to oxygen. So this is syn case. And when I will see hydrogen and OH, hydrogen and OH group are present on the same side, that is syn. When hydrogen and OH are present on the opposite side, that is anti. This is the case for aldooxymes. If I talk about ketooxymes, again what I will do is, okay, now with respect to R1 and OH, I would say it is a syn. But with respect to R, with respect to R and OH, it is anti. With respect to R dash OH, it is syn. With respect to R2 OH, they are on the opposite side, so they are anti. But with respect to R1, it is OH. Clear, students? Or you can take this as R1 and this is R2. Now, I am considering R2 and OH, so it is syn. R2 and OH on the diagonal, it is anti. If I take R1 and OH, it will be anti. R1 and OH, it will be syn. So with respect to which you take, it matters a lot, right? Okay, students, now comes the case for azoalkanes. Now, what are azoalkanes? Azoalkanes are the simplest one. Here you need to see when nitrogen is bonded with nitrogen, here is the lone pair, here is the lone pair, here is the G group, here is the G group. Now, this is basically syn. And one more case, if I take nitrogen, double bond nitrogen, G group. One second. This is anti when they are present on the diagonal side. Clear, students? So this was all about syn anti naming. Now we are going to find out the nomenclature. Which one? EZ nomenclature. We have done the naming. As I told you, EZ1 is the most important one. Now for the following cases, we will calculate the EZ naming. Now students, to identify E and Z naming, first of all we need to give the numbers. And to give them numbers, we need to see their atomic numbers, right? The atomic numbers, whose will be highest, will be given the priority, right? So if I see here again, here deuterium is there, so it will given first number, it will be given second number. Why, students? Because it is the heavier isotope. Now if I talk about this system, here what do I observe? Carbon is, if I open the system, the below one, carbon is attached to two hydrogens and attached to nitrogen, which is further attached to two hydrogens. It is somewhat like this. And if I talk about this system, which is NH double bond C. So how to open this? Carbon single bond nitrogen, which is further attached to hydrogen. It is making a double bond. So single bond is shown again. Now this nitrogen is also making a bond with carbon. So it is like this. Now to check for both of the cases, we are talking about this carbon and we are talking about this carbon. It is further attached to nitrogen, hydrogen, hydrogen. It is attached to nitrogen, nitrogen. So here nitrogen has atomic number more. So this students will be given, this will be given first priority, this will be given the second priority. So here now first and first number are present on the diagonal, that means they are enemies of each other, hence E nomenclature will be seen over here. Now let us see the next case. If I see this case, students, again I have triple bond over here and double bond over here. Let us open this system first. CH double bond CH2. To open it up, this is the carbon atom with whom it is attached. This carbon is attached. So it has hydrogen. It is further attached to CH2 single bond. Now to make a double bond, it is further attached. So it is further attached with carbon. Now this carbon is also making a bond with carbon. This is also making a bond with carbon, right? I am talking about this carbon. Now let us make for this case also, where we see carbon triple bond CH is there. Now first of all we will make a single bond like this. Now we know that this carbon is making two more bonds with carbon, so two more carbons will be attached over here, and this carbon is also making two more bonds with this carbon, so it is like this. Now let us see, here we are talking about this carbon atom, right? Now this carbon atom is further attached to what? Carbon, hydrogen, carbon, and it is attached to carbon, carbon, carbon. So here carbon has higher atomic number because two carbons are cancelled. Another one is carbon and hydrogen. So it has more atomic number. Hence it is 1 and it is 2. Now if I see both of these cases, again I am getting what here? Double bond. So I will open it. It will be attached to more carbon. So it will be given first number. It will be given second number. Hence I would say that 1 and 1 are present on the same side, students, over here. What I am observing over here? One second. There is a quite mistake which I did. I was talking about this, that it has 3 carbons and I have written 1 number over here. It is basically the 2 number. It is basically the 1 number. Right? We have seen for the triple bond it is 1. So kindly correct it. So 1 and 1 are present in the diagonal sides, and that means these are enemies of each other. So E nomenclature will come. Clear? Okay. Now let us see the next case. Okay, now for this case, first of all, here we have fluorine, here we have oxygen. And we know that, fluorine has higher atomic number, so it is 1, it is 2. Now, if I see this case, nitrogen has higher atomic number and carbon has lower atomic number. So 1 and 1 again are present on the opposite sides. That means it is E nomenclature. So students, hopefully you can now attempt all the questions based on the nomenclature. Now moving forward, we are doing about optical isomerism. Now we have covered geometrical isomerism in the section stereoisomerism. Now moving to the portion optical isomerism. Now, what do you mean by optical isomerism? Basically, in which chemical and physical properties are same except action on plane polarized light. What I said, chemical and physical properties physical properties are same except action on plane polarized light. Now, what I meant by plane polarized light, I will explain you with the help of the experiment that was conducted with the help of polarimeter. What happened? Ordinary light was taken, which was present in all of the directions. Ordinary light was taken. This is ordinary light. Students, this ordinary light was passed over. It was passed over the nickel prism. And the light which was perpendicular to this direction of propagation comes out to be the PPL, the plane polarized light. When it passed, we got only in this direction, that was PPL, the plane polarized light, which was, students, further passed from any organic compound, what we observed that this PPL, plane polarized light, gets rotated in two different directions. It was like this, it was like this. Now either it be rotated in this direction or it be rotated in this direction. Two cases were seen. When this case was seen, it is rotated in the left direction, so it is known as levorotatory, and when it is rotated in the right direction, it is known as dextrorotatory. Clear? So this was about how plane polarized light topic came upon and how we need to check the optical activity over here. So this was the experiment through which we got to know that during the plane polarized light, it was the situation when optical isomerism arised. Chemical and physical properties are same except action on plane polarized light, where its properties got changed because direction got changed. Either it is converted into left or it is converted into right. So we will see this very detailed concept each and every topic. First of all, we need to understand what is a chiral center. Chiral center basically is a center, or it is an atom which is sp3 hybridized atom which is connected to four different groups. Kindly mention this very clearly. It is sp3 atom which is connected with four different groups. The sp3 carbon is called as chiral carbon and sp3 atom is called as chiral center. Clear? Now you need to note down, presence or absence of chiral carbon is not any criteria for molecule to be optically active. This is not a criteria. First of all, what we need to find out, we will find out the chiral center over here. Chiral center is the one which is sp3 hybridized atom and has four different groups. So if I see this case, does this carbon has four different groups? No, it has three hydrogen over here to complete its valency, right? So it is not a chiral center. Okay, if I talk about this carbon, it has OH group, it has here over carbon, here it has carbon carbon chain, which is different. Here it is different, here it is different, and one is hydrogen. So yes, basically it has one chiral center over here, which is I have marked with a star. If I talk about this case, I see this carbon atom, it has methyl group, it also has a methyl group. CH3 or Me is almost equivalent, or I would say ET or CH2CH3 same. So we want four different groups. Hence there is no chiral center over here and there is a chiral center over here. Clear, students? So now you can easily identify the chiral centers. Now we will move forward towards our next topic, that is chiral object and achiral object. Chiral object are those that cannot be superimposed. For example, if I talk about my this hand and this hand, okay, these are mirror images of each other, but they cannot be superimposed. If I will superimpose them, my, see thumb, both thumbs are visible, right? So these cannot be superimposed. Chiral are the ones, chiral objects are the ones that cannot be superimposed. But students, achiral are the ones that can be superimposed. that can be superimposed. For example, if I talk about this pen and if I keep one pen same in front of it, so it will be a mirror image and it will be superimposable. So that comes under the category of achiral objects. Now let us take an example also. If I draw its mirror image over here, then this will be same COH, this CH3 will be same. Now OH will look here and hydrogen will be here. Now these are mirror images of each other, but are they superimposable? Kindly keep the structure on this, but you will see the difference that COH is placed over COH, CH3 is placed over CH3, but the difference is OH will be placed on H and H will be placed on OH. So hence it is not superimposable. Okay, and one more thing, students, that we need to keep in our mind: if two real molecules look like mirror images, they are non-superimposable, but it is not the condition that individually they are, individually they are active compounds. So first of all, we need to understand what are chiral carbon, then we need to understand the chiral objects and the achiral objects. Clear? Now next condition comes disymmetric molecule. Disymmetric molecule is basically the molecule from which two symmetry elements. Now these are two symmetry elements. One is plane of symmetry. Plane of symmetry. Another one is center of symmetry. These are the two symmetry elements that it's talking about. So molecule from which two symmetry elements are absent together are referred to as disymmetric molecule, and when these both are absent, the molecule is said to be optically active compound. Clear? So now students, let us see the very first case, that is plane of symmetry, or POS I would say. Plane of symmetry is an imaginary plane is present in a molecule along which molecule can be divided into two equal halves. Okay, and which are mirror images of each other. Let us take one example. If I take this example, students, so I would say we will pass one plane in this direction, so it will divide it into two equal halves and they are mirror images of each other, right? So it is what? It has a plane of symmetry over here. Now let us take one more example. If I say okay. Now, what do you mean by this? This means that the group is present towards the observer. For example, this is the compound and Cl are present in front of this like this. So, can you pass a plane? Yes, we can pass a plane over here and it will divide the molecule into two equal halves, which are mirror images of each other. Now, let us take one more example over here. If I say, now, is there any POS present over here? So no. Why no? Because here one Cl is present in front and one Cl is away from the observer. So it cannot divide the molecule into two equal halves. Now come students, the very next category, that is center of symmetry or COS. Now what do you mean by center of symmetry? The point present at the center of molecule through which if straight lines are drawn at equal distance in opposite direction, identical group must be present. Now let us take one example to clarify this. For example, students, we have this case. Now, what does it says? It says from the centermost position, move in the opposite direction. For example, I am moving in this direction, I am getting a carbon. I am moving in this direction, I am getting a carbon. Equal? Okay. If I move in this direction, I am getting a carbon. If I move in this direction, I am getting a carbon. Equal. Okay. If I move in this direction, I am getting a hydrogen. If I move in this direction, I am getting a hydrogen. Equal. If I move in this direction, I am getting a CH3. If I move in this direction, I am getting a CH3. That means equal. So the point from the centermost position to all the paths to all the opposite directions, if we get the identical group, that means it has a COS. That means here center of symmetry element is present. Clear? Okay students, now you have seen both of the symmetry elements, that is the plane of symmetry and this element center of symmetry. If both of these are absent, then the compound is said to be optically active. So we will take different cases and find out. So now you need to draw with me. Let us see the first case. For example, I have this case. Kindly tell me It has a chiral center or not? It has plane of symmetry or not? It has center of symmetry or not? And it is optically active or not? Okay, if I see this case, so first of all, to be chiral, it should have 4 different groups. So this carbon has 3 same groups, so it is not chiral. Now, to check the plane of symmetry, we should pass a plane and it should divide into 2 equal halves. So I will pass a plane in this direction. So it is divided into 2 equal halves. So yes, plane of symmetry is present over here. Now, if I talk about center of symmetry, so I will move from centermost position to the opposite directions. So if I move from this direction over here, hydrogen, over here, hydrogen. In the above direction, I am getting chlorine, and in the below, I am getting hydrogen. It should be upper also chlorine, lower also chlorine. So center of symmetry is not present over here. To be optically active, both of the elements should be absent, but here plane of symmetry is present, so it is not an optically active compound. Now let us take one more example over here, students. Carbon, bromine, hydrogen, fluorine, iodine. Okay. Now if I have this example with me, students, now kindly tell me, is there any chiral center? So yes, 4 different groups are present. So yes, it is a chiral center present over here. Now plane of symmetry is that it divides it into 2 equal halves. So it cannot divide into 2 equal halves. Either I cut in this direction or I cut in this direction. So no. Center of symmetry, no, because if you move in this direction, you are getting bromine. If you move in this direction, you're getting hydrogen. So equal atoms, same elements should be there. So it is not there. Now, when both of the elements are absent, the compound is said to be optically active. Hence, it is what? It is optically active. Now let us take one last case to understand this more easily. Okay. For example, I have this case. Now kindly tell me, is there any chiral center present over here? So if I see in this case, students, I have this carbon. This carbon should have 4 different groups. It has Br over here. It has one hydrogen. It has 2 different groups over here. If you move in this direction, you're getting something else. If you move in this direction, you're getting carbon and Br again, right? So yes, here chiral center is present. Here chiral center is present. Now here POS, plane of symmetry, is present. Yes. If I pass a line over here, so yes, plane of symmetry is also present. Now, is there any COS? No, because we have to move in opposite direction. If I'm getting BR here, I should get a BR in the opposite direction as well. So no, here plane center of symmetry is absent. So now, to be optically active, both of the things should be absent, but yes, plane of symmetry is present, so it is not an optically active compound. Now, I hope so you can easily identify optically active compounds, students. Okay. Now, moving forward, we are going to start projection formula. And for isomerism, for this lecture where we are covering, we require only 2 formulas to understand in depth. That is wedge dash formula, another one is Fisher projection formula. These 2 are the most important that we need to know for this lecture, but these 4 will come in your upcoming syllabus in 11th 12th that we will cover. Don't worry about it. For this lecture, first of all, what we need to do is we need to understand the wedge dash formula and the Fisher projection formula. So now let us take an example. If I say carbon has one group, COH group over here and CH3 group over below. Okay, now these 2 are in plane. One will be towards the observer, another will be away from the observer. So if I say here OH is present towards the observer and hydrogen is present away from the observer. So this is wedge dash projection formula. This is basically what? This is wedge and this is what? Dash. So wedge bond and dash bond is the wedge dash projection formula. Now to convert it into Fisher formula, what we need to do is we represent this carbon atom as like this. One second. This is referred to as this carbon atom. Now, as you know, it is present. Just place it over here, like COH is present over here. Okay, CH3 is present over here. Now, question arises, this OH and H. As you know, OH is towards you. OH is towards you and hydrogen is away from you, away from the observer. So if hydrogen is away from the observer, it is present over here, and OH is towards you, so it will be present over here. So this is the basic conversion that you should know. Now comes, students, the next thing, that is absolute configuration, which is referred to as RS configuration. RS configuration. As we did EZ nomenclature, similarly we have RZ configuration. Rules are quite same, but yes, it is quite different from the previous case. Here, what are the rules? Group whose first atom has higher atomic number is senior. Here also, who has higher atomic number is preferred as a senior group, which has a lower atomic number is preferred as a junior group. Now, in case when first atoms are common, now here we will look the cases in the Fisher projection formula. That's why I told you. Okay. In case when first atoms are common, then go for the second, third, and so on till the first point of difference is obtained. For example, students, for example, let us take a general case over here. Here COH is present, here OH is present, here CH3 is there, here H is there. Now, if I say, kindly tell me which is the first priority that you would give, you will say oxygen has the atomic number, more. So it is first number. Then we have here carbon, carbon same, it has oxygen, it has. We will move towards the second atom, oxygen and hydrogen. Oxygen will have more atomic number, it is second, it is third, and it will be referred to as fourth. So likewise, we will give the numbering based upon their atomic numbers, right? If I move forward towards the next rule, it is in case when first and second atom of the group are connected with double, triple bond, then hypothetically it is considered they are connected twice or thrice with each other, like we did in EZ. We opened up double bond, triple bond. Similarly, we have to do in such case. And again, lone pair is always the junior group, students. Clear? Now we will move towards the trick section that we need to know. First of all, listen the trick. On Fisher projection, if fourth group is present on the vertical line is this one, horizontal line is this one. If fourth group, you will number 1, 2, 3, 4. Fourth one is present on the vertical line, then you have to move from first number to the third number. Okay, and if you are moving in clockwise direction, then it is R. In clockwise direction, you are moving in clockwise direction, so it is R. In anti-clockwise direction, so it is S. For which case? When you see fourth group on vertical line. And when you see fourth group on horizontal line, students, then you will see what? You will see the opposite. Clockwise is basically then S and anti-clockwise will be R. You will always move from first number towards the third number. Clear, students? Okay. Now, students, let us see the next one, that is enantiomers basically. What do you mean by enantiomers? First of all, we shall take one example for this case, for the trick case, for you to understand more clearly. I would take an example. Let us take Cl over here, CH3 over here, and I would take hydrogen, and or the previous case also you can do, which we were doing, right? CH2H. Let us take this case. Now for this case, students, first of all we need to see, we know that chlorine basically has the highest atomic number, so it is referred to as 1. Now here you see carbon is the first atom, second and third atom is hydrogen over here. Here these are two hydrogen, but the third is oxygen over here. So this is second number, this is third number, and this is fourth number, right? So we know that fourth group is now present on the vertical, fourth present on the vertical. Move from 1 to 3. 1 direction, 2 direction, 3 direction. It is which direction? Clockwise. This is clockwise, like the clock moves, right? So when fourth is present on the vertical clockwise, it is referred to as which configuration? R configuration. It is referred to as which configuration? R configuration. It is quite simple. So likewise, you can do the following questions in your DPPs also and from the different books also. Now comes our next topic, students, that is enantiomers. What are enantiomers? Enantiomers are basically non-superimposable mirror images. These are basically non-superimposable mirror images, non-superimposable mirror images. Some, here what you observe is that same physical properties can't be separated by fractional distillation, and chemical properties remain same throughout. They have optical rotation in different directions as well. So these are the basic things that you should know about enantiomer, that same physical properties can't be separated. Same physical properties can't be separated by fractional distillation. Chemical properties also remain same throughout. Chemical properties remain same throughout. Okay. Now, if I see what are our diastereomer students, so I would say these are non-mirror images. They may be optically active. One of them may be optically active, another one is optically inactive, or both of them optically inactive. They can be separated by physical methods. So these are basically, these can be separated by physical methods, and yes, they are non-mirror images. They are non-mirror images. Clear, students? This was about diastereomers. They may be optically active, they may be optically inactive, or they may be, one of them may be optically active, another one may be optically inactive. Now, students, comes our next topic, that is conformers. It is going to be quite interesting topic because we will see 3D structures of the conformers of ethane, butane, likewise. Okay, so first of all we are going to do the conformers of ethane. So students, as we were doing conformers of ethane, so first of all we need to write the ethane molecule, that is CH3 single bond CH3. So how can I represent it? Carbon carbon, then I can represent all of the hydrogens in such a way. Clear? Now students, what I'm going to do is I'm going to represent them in the form of Newman projection formula. How to represent? Kindly observe very carefully. First of all, I'm going to represent my first carbon atom as a dot. This is my first carbon atom. I am representing it as a dot. And the second carbon atom, I am representing it as a circle. This is my second carbon atom, which I have represented as a circle. Now, the next thing which I need to do is, students, next thing which I need to do is to mention all the hydrogen atoms. As you can see, it has 3 hydrogen atoms over it. So, 1 hydrogen atom, 2 hydrogen atom, 3 hydrogen atom. Clear? Now, the next part is, the second carbon also have 3 hydrogens with it. Hydrogen, hydrogen, hydrogen. How does it actually look like? It actually looks like this. Kindly observe this structure very carefully. The black one represents the carbon atoms and the white ones are representing the hydrogen atoms. I am showing you in this way so that it is more clear to you. See, this is the front view which you have seen like this. See, this is basically the front view. Here you can see there is an angle between them. This is dihedral angle which is represented by theta. Here theta is equals to 0 degree. Why 0 degree? It is 0 degree like this. See, this is the first carbon atom, this is the second carbon atom. It is one after the another. So the angle between them is 0 degree. It is just to show you. That's why I have made it a bit slighter this away so that it is visible to you. And already written that theta is equal to 0. This form is known as eclipsed form. Eclipsed form. Now students, one more form is seen. If I rotate the second carbon atom with 60 degree like this, then you are able to see all the hydrogen atoms of the front carbon as well as of the back carbon. First of all, this situation was seen. Now you can easily see this situation, see all the hydrogen atoms. What is this? These are conformers. Conformers basically are generally seen in the case of single bond, because in single bond there is an easy rotation, while in double bond the bond breaks. That's why we are taking the very first case for the ethane, because here rotation is very easy. You can directly rotate the carbon atom. For example, I have taken this case in one after the another, which I have showed you. This is the eclipsed form. To make it staggered form, I am rotating it with 60 degree angle, the second one carbon. Now, how does it look like here? Now, let us draw the same structure over here. First of all, the first carbon is representing by a, big dot. Like this. The second one is being represented by a circle over here, right? Now the hydrogen atoms that are present over the first carbon atoms are, look, these are like this, these are like this, hydrogen, hydrogen, hydrogen. Now students, to make the hydrogen for the previous one, we have rotated it 60 degree, so it comes out to be like this, hydrogen, hydrogen, hydrogen. Now this angle is 60 degree. This angle is 60 degree. This looks like this. Clearly, it is clear to you. It is a staggered form. It is staggered form. Now students, from both of these forms, which is, stable. So I would say that in this case, what do we observe? We observe that here, these are present in such a way that the bonds create repulsion between them. Here there is repulsion. Here there is repulsion. So basically what happens here, it is less stable. And here there is no repulsion, less repulsion. So it is more stable. So it is more stable. Now students, as these were the Newman projection formula, now we will convert it into sawhorse projection formula. Now, how does sawhorse projection formula look like? See, this was the structure for the Newman. Now, to convert into sawhorse, we will tilt it a bit like this. How come? See, I have made this structure hydrogen, hydrogen, hydrogen. Here were hydrogen, 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 hydrogen. This was eclipsed one, right? Now, the staggered one looked like this. Hydrogen, 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 hydrogen. To make it in the form of sawhorse projection formula, what I'm going to do is, I'm going to put this as my first carbon atom, the bigger circle, this as my second carbon atom. It was like this. Now I am representing it like this. Clear? Now, it is making a, opposite Y like this for hydrogen atoms. Then this is the bond between the two carbon atoms. This is the bond between the two carbon atoms. Then again an opposite Y. So this is the sawhorse eclipsed form. Now to make the staggered one, again this is my first carbon, this is my second carbon. It looks like this. Kindly see this. Kindly see this. It looks like this. Now again, if I see, the front one has an opposite Y and the backward has the, Y shape like this. So it is the staggered form. Okay, for the sawhorse projection formula. Now comes the energy profile diagram. Now comes the energy profile diagram. Okay, students. Here we will write theta. That means dihedral angle on the x-axis over here. And on the y-axis, students, we are taking our potential energy. So as I told you, eclipsed form is less stable. So we'll have more potential energy. It will have more potential energy. And staggered form is more stable. So we'll have less potential energy. This is staggered form. It is eclipsed form. Okay. Now what we see from eclipsed form, when there was eclipsed form, it was 0 degree. When it came to be 60 degree, what we saw? Eclipsed converted into staggered at when 60 degree. Then again, if you rotate it 60 degree, it will convert it into eclipsed. When you will rotate again, it will convert it into staggered. When you will rotate again, like this. So this is the graph that is being observed, right? After every 60 degree, the forms get changed. After every 60 degree, the forms get changed. So this was the conformers of ethane that you need to know. Other than this, students, is propane. In propane, what case arises? Let me tell you. Let me take one methyl group over here to make you more understandable. See, if I replace my one hydrogen of ethane with methyl group, this group, then it is referred to as my propane. Clear? Because propane contains 3 carbon atoms, right? Now, Newman projection formula looks like this. I have to convert it into what? Simple projection formula looks like this. I have to convert it into Newman projection formula. So here what I'll do is, this is my first form, eclipsed form, when there is 0 degree angle. Now I will rotate the second carbon atom with 60 degree and I will obtain the staggered form. It is more stable because there is less repulsion, and it is less stable because here is more repulsion. Clear? Now again, if I'll draw its energy profile diagram, how it would look like, similar way, just that of ethane. Eclipsed will have more energy because it is less stable. Staggered will have less energy because it is more stable. After every 60 degree, the forms will get converted into each other. Now comes the last one, that is for the butane case, students. That is quite important. For N-butane, I would say basically these 4 structures can be obtained. In the previous cases, we saw 1 eclipsed form, 1 staggered form, but here 2 eclipsed form are seen and 2 staggered form. One is where when there is fully eclipsed. Okay, after that 60 degree rotation, you see gauge form, in which you can see there are 2 methyl groups which are present in such a situation. After then 60 degree, you find partially eclipsed form, and at last you will find anti form. Clear? So here 2 eclipsed form are seen, fully eclipsed, partially eclipsed, and one is gauge form and anti form that are a part of staggered form. So here what is the energy profile? Again, eclipsed form basically will have high energy because they are less stable, right? So they will have high energy first fully eclipsed, then partially eclipsed, then gauge form is stable, and then gauge form will have more energy, and then anti form. So the stability order is just opposite of the energy order, right? So at 0 degree, what was there? Fully eclipsed. Then at 60 degree rotation, gauge form was formed. Then at 60 degree rotation, this partially eclipsed was formed. Then at 60 degree rotation, which form was formed? Anti one. Then at 60 degree rotation, again which form was formed? Partial eclipsed. Then at 60 degree rotation, gauge form, and at last fully eclipsed. So basically this is the structure for the energy profile diagram. This I have written for stability order. Anti will be more stable because it has less energy, then gauge, then partially eclipsed, then fully eclipsed, and the opposite order is of energy. But students, what happens when there is hydrogen bonding? In that case, gauge will become more stable than anti when hydrogen bonding occurs. In that case, gauge will become more than anti. Gauge will become more stable than anti, and that effect is known as gauge effect. So students, this ends up our chapter here about isomerism. I hope so that you have learned a lot of concepts today. I just want that kindly apply the formulas of geometrical isomers or optical activity in the DPP as well, and try to attempt more and more questions for the examination sake from DPPs, from different books. And do let me know one homework I have given you. Kindly mention your name and the answer in the comment section. So before ending, I would just say, don't stress at all. Don't stress. Do your best. Forget the rest, and all the best, right? So I'll meet you in the next lecture in General Organic Chemistry. I wish you all the very best for your upcoming examination. Thank you so much. Keep smiling.